Hello there, and welcome to Life Beyond Seen, where the strangest things on this planet tend to be the ones hiding in plain sight, buried under ice, or drifting in the dark of an ocean no one visits. Imagine for a moment that you're looking at a map of Antarctica in the middle of winter. Not a summer map with its thin coastal fringe of open water and its dramatic cliffs of blue ice. A winter map. The kind where the sea ice spreads outward from the continent like a slow exhale, covering millions of square kilometres of ocean in a pale, continuous sheet. Everything frozen, everything locked. The Southern Ocean in winter is about as close to a sealed system as nature gets. Cold beyond most human reference points. Dark for months at a time, pressured by ice that can reach several meters thick. It is one of the most remote and least visited places on Earth, and for good reason. There is almost nothing there that is comfortable, and almost everything there that is extreme. And yet, in 1974, when scientists sat down to look at satellite images of exactly that frozen, sealed winter ocean, something was wrong. Right in the middle of the Weddell Sea, hundreds of kilometres from any coastline, surrounded on all sides by winter ice, there was a hole, not a crack, not a thin patch at the edge of the pack, a hole. A vast, open, liquid window in the middle of a frozen ceiling, roughly the size of New Zealand. Some estimates put it at around 250,000 square kilometres at its peak. That is larger than the United Kingdom. That is larger than most countries on Earth. And it was sitting there in the dead of Antarctic winter, in a place where open water should have been essentially impossible. Scientists did not know what to make of it, and in some important ways, nearly 50 years later, they still do not have the full picture. Tonight, we're going to spend some time with that hole, with what it is, how it forms, why it disappeared for almost 4 decades, and why it came back. We're going to go down into the layered structure of the Southern Ocean, visit an underwater mountain that almost no one has heard of, and think about what a patch of open water in one of the most isolated corners of the planet might mean for the climate of the entire Earth. It is a quieter kind of mystery than most. No lost civilization, no dramatic event, just physics and cold water and a planet doing something unexpected in a place where almost no one is watching. Before we go any further, I want to ask you something simple. Where are you right now as you listen to this? What is the temperature outside your window tonight? Because wherever you are, whether it is warm and humid or cold and clear or somewhere in between, the Southern Ocean is sitting at somewhere around minus 30 or 40 degrees Celsius right now in its winter months, and the ice out there is doing things that we're only just beginning to understand. There is something about knowing that, about holding that contrast in your mind, that makes the story feel a little more real. If you enjoy this kind of slow, careful storytelling, the kind that takes its time and goes somewhere worth going, it would mean a lot if you like this video and subscribe to the channel. It genuinely helps, and it lets us keep making these long, unhurried explorations together. There is no rush here. That is kind of the whole point. Now, let us start at the beginning, which in this case means starting with a satellite. The year is 1974. The Nimbus 5 satellite, launched by NASA in December of 1972, had been orbiting Earth for about 2 years. It was carrying an instrument called a microwave radiometer, a sensor that could detect microwave radiation emitted by the Earth's surface, which meant it could see through clouds and through the polar darkness in a way that ordinary optical cameras could not. This was a significant capability. Antarctica in winter is covered in clouds and shrouded in months of darkness, which makes traditional satellite photography essentially useless for studying the sea ice. But microwaves pass through clouds. They let you see the ice below regardless of what the sky is doing. Researchers processing the Nimbus 5 data noticed something in the Weddell Sea that did not fit. There was a region, large, unmistakable, impossible to dismiss as instrument error, where the microwave signature looked like open water rather than ice. And it was not near the coast. It was not at the edge of the pack where some opening might be expected. It was deep in the interior of the winter ice field, in a location that should have been as frozen as anywhere on the planet. The hole persisted through 1975. It persisted through 1976. 3 winters in a row, the same open patch, in roughly the same location, surrounded entirely by ice. And then, in 1977, it closed. The ice moved back in. The window shut. And for decades, nothing like it appeared again at that scale. The early reactions from the scientific community were, understandably, a mixture of fascination and confusion. Some researchers initially wondered whether there was a geothermal explanation, some kind of volcanic heat source on the seafloor pumping warmth upward. Others pointed to unusual current patterns or atmospheric anomalies, or some combination of factors that no one had properly characterized yet. The honest answer at the time was that no one really knew. The tools available in the mid-1970s to study deep ocean dynamics were limited. You could see the hole from space. You could not easily send instruments into the Weddell Sea in winter to figure out what was driving it. So the mystery sat there, half understood, filed away as one of the stranger things the Southern Ocean had produced. The feature, as scientists would come to call it, is a polynya. The word comes from Russian, Polynya, and it simply means a natural hole or opening in sea ice. Russian sailors and Arctic researchers had used the term for centuries, describing the patches of open water that sometimes appear in the Arctic Ocean, often near coastlines where winds push ice away from the land and leave stretches of open sea behind. Those coastal polynyas are relatively well understood. Wind pushes the ice offshore, open water is exposed, and the sea surface interacts directly with the cold air above. They are common enough that researchers have catalogued dozens of them around Antarctica and the Arctic, and they play important roles in local weather and ice formation. Coastal polynyas make sense. There is a mechanical cause you can point to. What makes the Weddell Polynya so different, and so much harder to explain, is that it is not coastal. It is an open ocean polynya, forming hundreds of kilometres from any land, with no obvious wind-driven mechanism to push ice away. The Weddell Sea in winter is a vast enclosed basin, and the ice that covers it is not being pushed anywhere by coastal geography. There is no shore nearby to create the kind of divergent flow that opens a coastal polynya. And yet, the hole appears anyway, year after year during that initial 3-year run, as if the ocean beneath simply refuses to freeze in that one location. The visual, if you could somehow stand above it, would be striking. Picture a white landscape extending to every horizon. Flat, pale, broken occasionally by ridges where ice flows have collided and buckled. And then, in the middle of that white expanse, a dark shape. Not grey dark the way thin ice looks, but genuinely dark. The colour of deep water. A roughly oval region where the ocean's surface is exposed, where small waves might be forming, where steam could be rising in the cold air as the relatively warmer water meets the frigid atmosphere above. It would look, as one researcher described it, like a window left open in a frozen ceiling, and through that window something from the deep ocean is reaching the surface. That something is what makes the Weddell Polynya one of the more remarkable features in modern oceanography. It is not a random anomaly, it is not a glitch in the satellite data. It is the surface expression of a process happening thousands of meters below. A process involving the layered structure of the ocean, a slow-moving circular current, and an underwater mountain that most people have never heard of. All of those things working together in a specific location, under specific conditions, to punch a hole through the winter ice and hold it open for months at a time. The Weddell Sea itself sits in a roughly triangular basin off the coast of West Antarctica, bounded by the Antarctic Peninsula to the west and the broader continent to the south. It is widely considered one of the coldest and most ice-covered bodies of water on Earth. Surface temperatures in winter can drop below -2 degrees Celsius, the freezing point of seawater, which is slightly lower than fresh water due to its salt content. The ice that forms here is not thin. In some areas, it reaches 2 or 3 meters in thickness, and in older, more consolidated pack ice regions it can be thicker still. Ships that venture into the Weddell Sea in winter do so carefully, if they go at all, because the ice can close around a vessel quickly and with enormous force. And yet, somewhere in the interior of that basin, roughly centred around a location near 65 degrees south and 3 degrees east, the ocean has a habit of doing something that defies the basic expectation of what a winter polar sea should look like. It opens. And it stays open. Not because of any single dramatic event, but because of a slow, deep, persistent process that the ocean has apparently been running on its own schedule for a very long time. Understanding why requires going a little deeper, literally. The ocean beneath the Weddell Sea is not a uniform body of cold water. It is layered, stratified, organised by temperature and salinity into distinct bands that do not easily mix. At the surface, the water is cold and relatively fresh, partly because sea ice formation and melting have shaped its composition over time. But below that cold surface layer, something warmer is hiding. A body of water called circumpolar deep water, which circulates around Antarctica at depth, is warmer and saltier than the surface water above it. Not warm in any comfortable sense, but warm relative to its surroundings. Warm enough, under the right conditions, to melt ice. In normal circumstances, that warm deep water stays down. The cold fresh surface layer sits on top of it like a lid, and the two do not mix because their density difference keeps them separated. The system is stable. The ice forms above, the warm water drifts below, and the two never really interact. But if something disrupts that stability, if the lid becomes thinner, or if some force from below pushes the warm water upward, then the deep heat can reach the surface. And when it does, it melts ice faster than the cold polar air can refreeze it. The Polynya opens, and because the convection becomes self-reinforcing once it starts, the Polynya can stay open for an entire winter season or longer. What triggers that disruption, and why it happens in one specific part of the Weddell Sea rather than somewhere else, is a story that involves ocean currents, seafloor geography, and a rotating column of water above an underwater mountain. It is a more complicated story than it might first appear, and it is one that scientists spent decades trying to piece together with limited data and limited access to the place where it all happens. But the basic shape of the mystery is already clear. There is a hole in the ice that should not exist. It appeared in 1974, stayed for 3 years, and then vanished. It left researchers with questions they could not easily answer, in a location they could not easily visit, using tools that were not yet good enough to see what was happening underneath. The hole became one of those problems that sits at the edge of scientific understanding for a long time. Known, documented, studied from a distance, but not fully explained. And then, 40 years later, it came back. And this time, the world was watching. But before we get to that, it helps to understand what a Polynya actually is in a more complete sense, not just as a visual feature, but as a physical process, and why the open ocean version is so much rarer and more puzzling than the coastal kind that researchers had been studying for generations, because the distinction matters. It is the difference between a feature that has a simple mechanical explanation and one that requires you to think about the entire vertical structure of the ocean, from the surface all the way down to the seafloor, to even begin to understand what you're looking at. The word Polynya comes from Russian. It means roughly a natural hole in ice, a gap that forms on its own, without any human cause, in a frozen body of water. Russian speakers, particularly those who spent time in Arctic waters, had a word for this long before satellite imagery existed, because they encountered it often enough to need one. Coastal polynyas are relatively common. They form near land, near ice shelves, near headlands and bays where the geography or the wind creates a persistent open patch. The wind pushes ice away from the shore, or upwelling near a coastline keeps the water slightly too warm to freeze completely, and you get a lead of open water that can last for weeks or months. Seabirds know about these openings. Penguins and seals use them. They are part of the normal ecology of polar regions, and while they are interesting in their own right, they are not deeply puzzling. There is usually a clear reason for them, and that reason is almost always tied to something physical and nearby. A coastline, a current close to land, a prevailing wind direction that happens to push ice away from a particular bay. Open ocean polynyas are different. They form far from any coast, in the middle of a frozen sea, with no obvious mechanical cause sitting right next to them. There is no nearby headland deflecting the wind. There is no shallow coastal upwelling to explain it. The open water simply exists, hundreds of kilometres from the nearest land, surrounded on all sides by ice, in the middle of winter. That is already strange. But what makes the Weddell Polynya particularly strange, even among open ocean polynyas, is its size. Most open ocean polynyas that researchers have documented elsewhere in the Southern Ocean are relatively modest, a few thousand square kilometres perhaps, appearing briefly and then closing. The Weddell Polynya in the 1970s reached roughly 250,000 square kilometres at its largest. To give that some scale, that is an area larger than the United Kingdom, larger than the state of Oregon. It is, by a significant margin, the largest open ocean polynya ever directly observed, and it sat in the middle of one of the most thoroughly frozen seas on Earth, in the dead of Antarctic winter, and stayed open for 3 consecutive years. That is the thing that makes it genuinely unusual. Not just that it formed, but that it persisted. A brief opening that closes after a few days might be explained by a storm, a temporary current anomaly, a short-lived pulse of warm water reaching the surface. But 3 years of continuous open water, in roughly the same location, through 3 consecutive winter seasons, that requires something more sustained, something structural, something built into the ocean at that location in a way that keeps the process running even as the atmosphere above is doing everything it can to freeze the surface back over. The cold air temperatures in the Weddell Sea during winter are not mild. They drop well below -20 degrees Celsius for extended periods. The heat loss from an open patch of water that size is enormous. Estimates suggest the Polynya was losing something on the order of hundreds of watts per square metre to the atmosphere during the coldest periods. That is a tremendous amount of energy being pulled out of the ocean, and yet the water kept not freezing, which means something from below was continuously replacing that lost heat, feeding the open surface with enough warmth to stay liquid through conditions that should have sealed it over within days. Coastal polynyas, even large ones, do not typically require this kind of explanation. The wind does the work. It pushes ice away mechanically, and as long as the wind keeps blowing in the right direction, the open water persists. Remove the wind, and the ice closes in. The mechanism is external and relatively straightforward, but the Weddell Polynya is not maintained by wind. Wind certainly plays a role in shaping it, in pushing its edges around, in influencing when and how strongly it opens. But wind alone cannot explain a 250,000 square kilometre hole in the middle of a frozen sea. The mechanism has to be internal. It has to be coming from the ocean itself, from below the surface, from somewhere deep enough that the cold atmosphere above cannot simply shut it down. This is what makes the open ocean type so much harder to explain, and so much more scientifically interesting. When you study a coastal polynya, you're mostly studying the interaction between the atmosphere and the surface ocean, how wind and air temperature shape the ice edge. When you study the Weddell Polynya, you're studying the vertical structure of the entire water column, from the seafloor to the surface, and asking how heat moves upward through a system that is normally designed to prevent exactly that. It is a fundamentally different problem, and it requires a fundamentally different set of tools and concepts to approach it. Other parts of the Southern Ocean do occasionally produce open ocean polynyas, though none at the scale of the Weddell. The Cosmonaut Sea, east of the Weddell, has shown smaller open ocean features in some years. There have been brief openings in other parts of the Antarctic ice pack that researchers have noted and catalogued, but these tend to be smaller, shorter-lived, and less consistently located than the Weddell event. the Weddell Polynya keeps returning to roughly the same place. That specificity, that geographic stubbornness, is one of its defining characteristics, and it is a clue. Something about that particular location makes it more vulnerable to this kind of opening than anywhere else in the region. The ocean there has a specific weakness, a specific point where its normal stratification can be disrupted more easily than elsewhere, and that weakness is tied to what sits beneath it on the sea floor. But even setting aside the mechanism for a moment, the visual reality of the Polynya is worth sitting with. Imagine flying over the Weddell Sea in winter, if you could, which in practice almost no one does. Below you, in every direction, is white. The sea ice stretches to the horizon, broken here and there by pressure ridges where ice sheets have collided and buckled upward, but essentially continuous, essentially featureless in its whiteness. And then, at a certain point, the white stops. Below you is dark water. Not a thin lead, not a narrow channel, but an enormous expanse of open ocean. Dark blue-grey, slightly steaming in the cold air as the relatively warm water meets the frigid atmosphere, its surface ruffled by wind in a way that ice never is. The boundary between ice and open water would be sharp in places, gradual in others, with broken flows of ice floating at the edges where the two zones transition, and that open water would extend in every direction for hundreds of kilometres before the ice began again on the other side. It would look, from above, exactly like a hole, a window in the ice, and the darkness below it would feel, in some strange way, like depth made visible. Like you're looking not just at the surface of the ocean, but somehow into it, through it, all the way down to whatever is driving it open from below. That image, the dark window in the white ceiling, is actually a useful one for thinking about what the Polynya is doing physically. It is not just an absence of ice. It is an opening through which the ocean and the atmosphere are exchanging enormous amounts of energy, heat, moisture, and gas. When the ice is present, it acts as an insulating layer between the ocean and the air. It slows heat loss, it limits evaporation, it prevents the direct exchange of gases like carbon dioxide between the ocean surface and the atmosphere. When the Polynya opens, all of that changes. The ocean is suddenly exposed. Heat pours out into the atmosphere. Water evaporates, adding moisture to the air above, influencing weather patterns across the Southern Ocean. Carbon dioxide and other gases move between the ocean and the atmosphere in ways that are still being measured and debated. The Polynya is not a passive feature. It is an active exchange point, a place where the deep ocean is communicating directly with the sky, and the effects of that communication ripple outward in ways that extend well beyond the Weddell Sea itself. There is also something worth noting about the word itself, Polynya, and what it represents in the history of polar research. The term entered scientific literature through the tradition of Russian Arctic exploration and research, which was extensive and often predated Western scientific engagement with polar oceanography. Russian scientists and navigators had been documenting sea ice features in the Arctic for a long time, and their vocabulary for describing those features was more precise and more detailed than what existed in English or other Western scientific languages. Polynya was one of the terms that transferred directly into international scientific use, unchanged, because it described something for which no equally precise English word existed. It is a small linguistic detail, but it reflects something real about the history of polar science, that knowledge of these regions was built up by many different national traditions, often independently, and that the vocabulary of the field carries traces of that history. When a researcher today publishes a paper about the Weddell Polynya, they're using a Russian word that was coined by people who sailed wooden ships into Arctic ice in the 19th century and needed a precise way to describe what they were seeing. There is something quietly pleasing about that continuity. What those 19th century observers could not have imagined, of course, is the scale of the Weddell Polynya, or the depth of the mechanism driving it. The coastal Polynyas they documented were, by comparison, small and mechanically simple. The Weddell version sits in a different category entirely. Not just larger, but driven by processes that operate at a scale and a depth that required modern oceanography to even begin to understand. It took satellites to see it. It took deep water instruments to begin measuring what was happening beneath it. And it took decades of theoretical work on ocean stratification, convection, and seafloor topography to build a framework for explaining why it forms where it forms and why it keeps coming back. The contrast between coastal and open ocean polynyas is, in a sense, the contrast between the simple and the genuinely puzzling. Coastal polynyas are solved problems more or less. Open ocean polynyas, and the Weddell Polynya in particular, are not. They sit in that interesting scientific space where the basic phenomenon is well documented, but the full explanation is still being assembled piece by piece from instruments deployed in one of the most difficult research environments on Earth. That space, between observation and full understanding, is where a lot of the most interesting science lives, and it is where the Weddell Polynya has been sitting since the first satellite images came back in 1974, and researchers looked at them and thought quietly that something was very wrong with what they were seeing. Or perhaps not wrong exactly, just unexpected. Just something the ocean was doing on its own, without asking anyone's permission, in a place where almost no one was watching. And the first time anyone actually did watch, the first time a satellite passed overhead with the right instruments at the right time of year, and the data came back clearly enough to see, what they found was a hole the size of a country, sitting in the middle of the winter ice, completely open, as if it had always been there, as if it were entirely normal, which in its own way, for the ocean, it perhaps was. The ocean has been doing this for a long time. Humans simply had not been looking long enough, or with the right tools to notice. And the story of how they finally did notice, what satellite first captured it, what the researchers who processed that data actually saw, and what they thought in those first moments of confusion, is where the history of this particular mystery really begins. The satellite that first saw it was not looking for it. That is worth holding on to for a moment, because it changes the texture of the discovery slightly. This was not a targeted search. No one had predicted that something like this would be there. The Nimbus 5 satellite, launched in December 1972, was designed primarily to study atmospheric temperature profiles and the general properties of the Earth's surface as seen from orbit. It carried several instruments, but the one that mattered for this story was a microwave radiometer, a device that detects naturally emitted microwave radiation from the surface below. What made this instrument particularly useful in polar regions was that microwaves pass through clouds. Ordinary visible light cameras are useless over Antarctica in winter because the cloud cover is almost constant and the light is almost non-existent for months at a time. But microwave radiation comes through regardless, and the radiometer could detect it day or night, through overcast skies, across the full darkness of the Antarctic winter. Ice and open water emit microwave radiation differently. Ice is colder and has a distinct microwave signature. Open water has another. The radiometer could tell them apart. And so when researchers began processing the data coming back from Nimbus 5, they could for the first time actually map the extent of Antarctic sea ice during winter, not just guess at it, not just extrapolate from the edges where ships occasionally ventured, but see it more or less directly from space. What they saw in 1974 was not what they expected. In the Weddell Sea, deep in the heart of the Antarctic winter, in a region that should by every reasonable expectation have been locked under solid sea ice, there was a gap. A large one. The open water region they identified stretched across roughly 250,000 square kilometres at its peak, an area comparable to the entire country of New Zealand, or slightly larger than the United Kingdom. It was not near a coastline. It was not in a region where any obvious mechanical process could explain it. It was sitting in the middle of the pack ice, hundreds of kilometres from land, surrounded on all sides by frozen ocean, and it was open. The water was dark and exposed and liquid, in the middle of an Antarctic winter, in one of the coldest places on the planet. The researchers who processed that data did not immediately know what they were looking at. Some initially wondered whether there was a calibration error. whether the instrument was misreading the surface type, confusing something about the ice structure for open water. But the signal was too strong and too consistent for that. This was not noise. This was a real feature. Something was genuinely open down there. The hole persisted. It did not close after a few days. It did not drift and dissipate. Through the winter of 1974, it held its position in the Weddell Sea. And then, when the following winter came, in 1975, it was there again, same general location, same general scale, same open water in the middle of the winter ice pack, as if the ocean had simply decided that this particular patch of sea would not freeze, regardless of the temperature above it. By 1976, it had become something that researchers were actively watching, a recurring feature, a mystery that was not going away on its own. Some of the early scientific discussions from this period have a particular quality to them, a kind of careful uncertainty that is different from ordinary scientific caution. These were oceanographers who understood sea ice reasonably well, who had frameworks for thinking about how polar oceans behaved, and what they were looking at did not fit comfortably into any of those frameworks. The Weddell Sea in winter was supposed to be frozen. That was not a casual assumption. It was based on the physics of the region, the air temperatures, the basic thermodynamics of seawater. And yet here was this enormous open patch of water, sitting there calmly, defying the expectation. The early hypotheses were varied, and some of them now seem a little optimistic in their simplicity. One early suggestion was geothermal activity, volcanic heat rising from the sea floor, warming the water from below and preventing freezing. This was not unreasonable as a first guess. There are geothermally active regions in the Southern Ocean, and if something were releasing heat from the seafloor directly beneath this location, it could theoretically keep the surface from freezing. But the scale of the feature made this difficult to sustain as a primary explanation. Geothermal venting is real, but the heat flux from known seafloor vents is generally far too small to maintain an open water region of 250,000 square kilometers through an Antarctic winter. The numbers did not work. Another early hypothesis involved unusual atmospheric circulation, the idea that persistent winds or some anomaly in the weather patterns above the Weddell Sea were preventing ice formation or driving ice away from the region. This was also investigated and also found insufficient. The winds in the area were not consistently strong enough or consistently directed in the right way to explain an opening that large, that stable, for that long. A third line of thinking pointed toward ocean currents, the possibility that unusually warm water was being transported horizontally into the region from somewhere else. This was closer to the truth, but still not quite the right picture. The mechanism, it would turn out, was vertical rather than horizontal. The warmth was not coming from the side, it was coming from below. None of these early explanations fully satisfied the researchers working on the problem, and in a sense that was appropriate because none of them were fully correct. What was actually happening in the Weddell Sea was considerably more interesting and considerably more physically complex than any of the initial hypotheses suggested. But in 1974, 1975, and 1976, the tools needed to properly investigate the subsurface ocean in that region simply did not exist in the form they would later take. Satellite imagery could show the surface. Ships could, in principle, reach the area, though the logistics of operating a research vessel in the Weddell Sea in winter were and remain extremely challenging. What was happening in the water column below the Polynya, at depths of hundreds or thousands of meters, was essentially invisible to the researchers trying to understand it. They could see the hole. They could not yet see what was making it. And then, in 1977, it closed. The winter of 1977 arrived, and when the satellite data came back, the Weddell Polynya was not there. The ice had closed over the region that had been open for 3 consecutive winters. The gap was gone. The ocean surface in that part of the Weddell Sea looked, from space, like it was supposed to look in winter. Frozen, white, featureless. Whatever had been driving the Polynya open had apparently stopped, or weakened, or shifted in some way that was not obvious from the surface data available at the time. The closure was almost as puzzling as the opening had been. If the Polynya was being maintained by some persistent physical mechanism, geothermal heat, a fixed current pattern, a permanent feature of the ocean circulation, then why would it simply stop? Fixed mechanisms do not turn off, but the Polynya had turned off, which meant the mechanism driving it was not fixed. It was variable. It was sensitive to something that had changed between 1976 and 1977, and whatever that something was, the researchers of the late 1970s did not yet have the data to identify it precisely. The scientific literature from this period reflects a genuine state of uncertainty. Papers were published describing the phenomenon, mapping its extent, proposing and evaluating possible explanations. The 1974 to 1976 Weddell Polynya was recognised as significant, something that had implications for Southern Ocean heat budgets, for sea ice dynamics, potentially for global ocean circulation. But the closure in 1977 introduced a new layer of ambiguity. Was this a regular, recurring phenomenon? Was it a rare anomaly that had happened to occur 3 years in a row and might not happen again for a very long time? Was it driven by a cycle in the ocean itself, or by random variability in atmospheric conditions, or by some combination of factors that would be extremely difficult to disentangle? These questions did not have clear answers in 1977, and in some respects they still do not have fully clear answers today, though the picture has become considerably sharper. What the closure did, in a practical sense, was make the Polynya much harder to study. A phenomenon that exists can be measured, at least in principle. A phenomenon that has stopped existing can only be analysed from the data that was collected while it was active. And in the mid-1970s, that data was relatively limited. Satellite microwave radiometry had shown the surface feature. The subsurface had barely been touched. The years after 1977 were, for researchers interested in the Weddell Polynya, a period of theoretical work more than observational work. The basic physical concept of open ocean convection, the idea that under certain conditions the deep, warm water of the Southern Ocean could rise to the surface and maintain an ice-free region, was developed and refined during this period. Theoretical oceanographers worked out the mechanics of how stratification in the water column could be disrupted, how convection could become self-sustaining once it started, and how the specific geometry of the Weddell Sea might make it a particularly favourable location for such events. This theoretical framework was genuinely important because it provided a way to think about the Polynya that was more physically grounded than the early geothermal or atmospheric hypotheses. But theory without current observations has limits. The Polynya was not there to test ideas against. It had closed, and the ocean was keeping its own counsel about when or whether it would open again. There is something mildly frustrating about that situation from a scientific standpoint. You have identified a phenomenon. You have recognised that it is important. You have begun to develop a theoretical framework for understanding it. And then the phenomenon itself disappears, taking with it the opportunity to test your ideas against reality. It is a little like finally having a question to ask someone, and then watching them walk out of the room. The question stays with you. The answer waits somewhere else. For the researchers who had been watching the Weddell Polynya through the 1970s, the closure in 1977 was not a resolution. It was a suspension. The mystery did not end. It simply went quiet. And the ocean, as it tends to do, gave no indication of when it planned to resume the conversation. That silence would last, more or less, for nearly 4 decades. Long enough that a generation of oceanographers would grow up studying the 1970s event as historical data, something that had happened before their careers began, something they could analyse and model and theorise about but could not directly observe. The question of what had caused the Polynya and what had closed it, and whether it would return, remained open in the scientific literature in a way that was unusual for a feature of this scale. Most large oceanographic phenomena are either persistent enough to study continuously, or rare enough that their absence is expected. The Weddell Polynya occupied a strange middle ground. large enough to be globally significant, but intermittent enough to be genuinely difficult to understand. And that intermittency, that pattern of appearing and disappearing on a timescale that did not match any obvious forcing mechanism, was itself one of the most interesting things about it. The ocean was doing something here, in this particular location, for reasons that had to do with the deep structure of the water column and the specific topography of the seafloor beneath it. Understanding those reasons would require better instruments, better models, and, eventually, the patience to wait for the Polynya to come back. Which, in the end, it did. To understand why the Polynya keeps returning to the same patch of ocean, and why it forms there rather than somewhere else in the vast expanse of the Weddell Sea, you have to look beneath the surface, not just a few meters down, but thousands of meters down, all the way to the sea floor. Because the answer is not written in the ice, or in the atmosphere, or even in the currents near the top of the water column. The answer is written in the shape of the ocean bottom itself. The Weddell Sea is, in basic terms, a large embayment on the Atlantic side of Antarctica. It is bounded to the west by the Antarctic Peninsula and to the east by a long stretch of the Antarctic coastline, and it opens northward into the broader Southern Ocean. In terms of sheer cold, it is among the most extreme ocean basins on Earth. Winter air temperatures over the Weddell regularly fall below -30 degrees Celsius. The sea ice that covers it in winter can reach several meters in thickness. Even in summer, large portions of the Weddell remain ice-covered, and the water beneath is some of the coldest anywhere in the open ocean. It is not a gentle place. It is not a place that invites easy study. Everything about the Weddell Sea, from its weather to its ice, to its remoteness from any port, tends to discourage close examination. But beneath all of that cold and ice and difficulty, the Weddell Sea has a circulation system of its own, a large, slow, rotating current called the Weddell Gyre. This gyre is not a small feature. It spans most of the Weddell Basin, covering an area roughly comparable to the continental United States. It rotates in a clockwise direction when viewed from above, driven by a combination of wind patterns and the Coriolis effect, the tendency of moving water and air to curve due to the Earth's rotation. The gyre is not fast. It does not move like a river or a tidal current. It moves slowly, steadily, turning over on a time scale of years rather than days. But it is persistent, and it is powerful in the quiet way that large, slow things are powerful. What the Weddell Gyre does, among other things, is transport water. It pulls water from the edges of the basin toward the centre, and it moves water at different depths in different directions. One of its most consequential effects is that it draws relatively warm, salty water upward from depth in certain parts of the basin. This is called upwelling, and it happens in many parts of the ocean wherever circulation patterns force deeper water toward the surface. In most of the Weddell Sea, this upwelling is modest and does not dramatically affect the sea ice above. But in one particular location, the upwelling tendency of the gyre is concentrated and amplified by something sitting on the seafloor directly beneath it. That something is Maud Rise. Maud Rise is an underwater seamount, essentially a submerged mountain, located in the eastern Weddell Sea at roughly 65 degrees south latitude and 3 degrees east longitude. It rises from the surrounding seafloor, which sits at depths of around 4,000 to 5,000 meters, to a summit that reaches to within about 1,600 meters of the ocean surface. That means Maud Rise stands approximately 3,000 meters tall measured from its base. It is not a small feature. On land, a mountain 3,000 meters tall would be noticeable. Underwater, it is enormous, a massive topographic obstacle sitting directly in the path of the Weddell Gyre's circulation. The name comes from the Norwegian ship Maud, which sailed through these waters in the early 1920s during an Arctic and Antarctic expedition, led by Roald Amundsen. The seamount was identified and named decades later, once ocean mapping technology had advanced enough to reveal the seafloor topography of the Weddell Basin in any detail. For most of the 20th century, the seafloor beneath the Weddell Sea was poorly mapped. partly because the ice cover made acoustic surveying difficult, and partly because the region simply did not receive much scientific attention. The discovery that there was a significant seamount sitting almost directly beneath the location where the 1974 Polynya had formed was, when researchers began to piece it together, not a coincidence. It was a clue. Here is why moored rise matters. When a large-scale ocean current like the Weddell Gyre encounters a seamount, a tall fixed obstacle rising from the seafloor, the flow does not simply pass over it the way water flows over a submerged rock in a stream. At the scales involved in ocean circulation, and given the influence of the Coriolis effect, something more interesting happens. The water tends to form what fluid dynamicists call a Taylor column, a rotating, roughly cylindrical structure of water that sits above the seamount and behaves somewhat differently from the surrounding ocean. The concept comes from work done by the British physicist Geoffrey Ingram Taylor in the early 20th century, and while the mathematics involved are not simple, the basic idea is not too difficult to picture. The seamount disrupts the normal flow of the gyre, and the Coriolis effect causes the disrupted water to spin in place above the topographic feature, creating a semi-isolated column that can trap water with particular properties. What this means for the Weddell Polynya is significant. The Taylor column above moored rise tends to concentrate water that has specific characteristics, in particular, water that is slightly less stratified than the surrounding ocean. Stratification, in oceanographic terms, refers to the degree to which the water column is divided into distinct layers that resist mixing. A strongly stratified water column has a stable, dense layer near the surface that acts as a lid, preventing the warmer, saltier water below from rising. A weakly stratified water column has a thinner or less effective lid, making it easier for the deeper water to reach the surface. The Taylor column above moored rise tends to draw together water that is already on the weaker end of the stratification spectrum, and it holds that water in place, concentrated above the seamount, where the gyre's upwelling tendency is also strongest. The result is that moored rise creates a preferred location, a kind of recurring weak point in the ocean stratification, where the conditions for deep convection are more easily met than anywhere else in the Weddell Sea. It is not that convection is inevitable above moored rise. It is that if convection is going to happen anywhere in the Weddell Basin, moored rise is where the threshold is lowest. The seamount does not cause the Polynya by itself, but it sets the stage. It makes a particular patch of ocean persistently more vulnerable to the kind of disruption that can allow warm, deep water to punch through to the surface. This explains something that might otherwise seem puzzling. Why the Polynya forms in roughly the same location each time it appears. If the phenomenon were driven purely by random atmospheric variability, a particularly strong storm, an unusual wind pattern, you would expect it to appear in different places in different years, wherever the atmospheric forcing happened to be strongest. But the Weddell Polynya does not appear randomly. It appears, when it appears, in the vicinity of moored rise. The seamount acts as an anchor point, a fixed geographic feature that biases the ocean's behaviour toward a particular location, regardless of what the atmosphere is doing on any given year. The atmosphere may provide the trigger, but the topography determines the address. Researchers studying moored rise have found that the strength of the Taylor column effect is not constant. It varies with the strength of the Weddell Gyre itself. When the gyre is circulating more vigorously, the Taylor column above moored rise is more pronounced, and the concentration of weakly stratified water above the seamount is stronger. When the gyre weakens, the Taylor column effect diminishes, and the preferred weak point above moored rise becomes less distinct. This gyre variability operates on timescales of years to decades, driven by a combination of wind forcing over the Southern Ocean and longer-term shifts in the ocean's salt and heat content. It is, in other words, a slow oscillation, not something you would notice from year to year, but something that accumulates over time and eventually tips the balance in one direction or another. This is one piece of the answer to the question that was left hanging after the Polynya closed in 1977. Why did it stop? If moored rise is always there, and the Weddell Gyre is always circulating, why does the Polynya not simply remain open? The answer is that while the seamount is indeed always there, the conditions that allow it to act as a trigger for deep convection are not always present. The gyre's strength varies. The stratification of the water column above moored rise varies. The amount of fresh water in the surface layer, which affects how easily the stratification can be broken, varies. The Polynya requires not just the presence of moored rise, but a particular configuration of all these other factors at the same time. When that configuration is in place, the seamount tips the system over the edge. When the configuration shifts, the mechanism loses its force, and the Polynya closes. There is something almost mechanical about this picture, once you understand it. Not mechanical in the sense of being simple. The Weddell Gyre, the Taylor column dynamics, the stratification of the water column, and the atmospheric forcing all interact in ways that are genuinely complex, but mechanical in the sense that there are identifiable parts, with identifiable functions that work together to produce the Polynya under the right conditions. The seamount is not magic. The gyre is not mysterious in any supernatural sense. They are physical features operating according to physical laws. What makes the Weddell Polynya feel almost mysterious is that the conditions required to set these mechanisms in motion are rare enough that decades can pass without them aligning. And then, when they do align, the result is a hole in the ice the size of a small country, opening in the middle of one of the most remote and frozen seas on Earth. It is worth pausing on the scale of moored rise for a moment, just to keep things in proportion. 3,000 metres is roughly the height of some of the taller peaks in the European Alps. Imagine a mountain of that size sitting on the bottom of the ocean, invisible from the surface, covered in perpetual darkness and cold, exerting its influence on the circulation of the water above it, not through any dramatic action, but simply by being there, by being a fixed shape in the path of a slow, enormous current. The water does not know the mountain is there in any sentient sense, of course. It simply responds to the topography the way fluid always responds to obstacles, following the rules of pressure and rotation and density. But the cumulative effect of that response, over years and decades, is a recurring pattern in the sea ice thousands of meters above, a hole that opens in the same general location, for reasons that trace all the way back to the shape of the seafloor. That connection between the deep topography and the surface ice, between a submerged mountain and an open water region visible from space, is one of the things that makes the Weddell Polynya genuinely interesting as a scientific object. It is not just a hole in the ice. It is a surface expression of processes happening at every depth of the ocean, simultaneously, from the seafloor to the atmosphere, all connected through the physics of fluid motion and heat transfer. Understanding the Polynya requires understanding all of those layers at once, which is part of why it took so long to develop a clear picture of what was happening. But even with moored rise identified as a key player, and even with the Taylor column dynamics reasonably well understood in theoretical terms, there remained a gap between theory and observation that would persist for a long time. The seamount is always there. The gyre is always circulating. The basic physical ingredients for a Polynya are always present in some form, but the Polynya itself is not always present. Something has to change. Some threshold has to be crossed. Some configuration has to come together before the mechanism activates. And identifying that threshold, understanding what pushes the system from a state where the Polynya does not form to a state where it does, requires something that the physical geography of moored rise alone cannot provide. It requires understanding what is happening in the water column itself, the layered structure of the Southern Ocean, the specific temperatures and salinities at different depths, and the way that structure can be disrupted when conditions are right. That is where the story goes next. So let us go down into the water, not in any dramatic sense, just in the way that oceanographers think about it, layer by layer, starting from the surface and working downward into the cold and the dark. Because the key to understanding why the Weddell Polynya forms, and what keeps it open once it does, lies in the structure of the ocean itself. Not the surface you can see from a satellite, but the invisible architecture of the water column below, the way different layers sit on top of one another, separated by differences in temperature and salt, each one influencing what the others can do. The Southern Ocean, like most of the world's oceans, is not a uniform body of water. It is layered. At the surface, you have water that is cold and relatively fresh, freshened by snowmelt, by precipitation, by the seasonal melting of sea ice. This surface layer is light because cold, fresh water is less dense than the warmer, saltier water beneath it. And that density difference matters enormously because it is what keeps the layers separated. The cold, fresh water floats. The warmer, saltier water below it sinks, or rather stays put, because it is denser and cannot rise easily through the lighter layer above. Below that cold surface layer, at depths ranging from a few hundred to roughly 1,000 meters depending on where you are in the Weddell Sea, there is a water mass that oceanographers call circumpolar deep water. This is water that has been circulating in the deep Southern Ocean for a long time, and it carries a memory of warmer conditions from elsewhere. Its temperature is not warm in any ordinary sense. We're talking about something in the range of roughly 1 to 2 degrees Celsius above the freezing point of seawater. That sounds like almost nothing. But compared to the surface water in the Weddell Sea during winter, which can be at or very near freezing, that 1 or 2 degrees represents a significant reservoir of heat. There is enough thermal energy in the circumpolar deep water, if it were to reach the surface, to prevent ice from forming, or to melt ice that has already formed, across a very large area. Below the circumpolar deep water, deeper still, you have Antarctic bottom water. This is among the densest, coldest water on Earth, formed when surface water in certain locations becomes cold and salty enough to sink all the way to the sea floor. Antarctic bottom water is important for reasons that go well beyond the Weddell Sea. It drives global ocean circulation in ways that affect the entire planet. But for now, what matters is where it sits in the stack, at the very bottom, dense and cold, beneath everything else. So you have 3 broad layers: a cold, fresh lid at the surface, a slightly warmer and saltier layer in the middle, and the very cold, dense water at the bottom. In normal conditions, this arrangement is stable. The surface lid is lighter than what is below it, so it stays on top. The warm circumpolar deep water stays in the middle, insulated from the surface by the cold, fresh layer above it. The heat it carries never reaches the surface. The ice above forms and persists through winter without anything below to disturb it. This is how the Weddell Sea behaves most of the time: a frozen surface, a hidden warmth below, the two separated by a thin but effective barrier of cold, fresh water. The question is, what happens when that barrier is weakened? If the cold, fresh surface layer becomes thinner, or saltier, or both, its density increases. And if its density increases enough, the difference between the surface layer and the circumpolar deep water below becomes smaller. The separation becomes less stable. It takes less energy to mix the 2 layers together. And if mixing begins, if the warmer water below starts to work its way upward, something interesting happens. The warm water releases heat as it rises, warming the water around it, but it also becomes less dense as it rises into the lower pressure environment near the surface, which encourages it to keep rising. And as it rises, it melts ice at the surface, which releases fresh water. But the mixing process simultaneously brings saltier water up from below, which can partially offset the freshening effect. The convection becomes self-reinforcing. Once it starts, it tends to keep going. This process is called deep convection, and it is the core physical mechanism behind the Weddell Polynya. When the stratification of the water column breaks down enough that the circumpolar deep water can begin rising, the heat it carries reaches the surface and prevents ice from forming. The open water then absorbs solar radiation during the brief Antarctic summer, and loses heat to the atmosphere during winter, but the convective supply of heat from below is large enough that the surface stays above freezing even when the air temperature above is far below it. The Polynya is not simply a hole where ice melted and did not refreeze. It is a location where the ocean is actively pumping heat upward from depth, maintaining an open water surface against the relentless cold of the Antarctic winter atmosphere. The heat flux involved is not trivial. Estimates from the 1974 to 1976 Polynya event, reconstructed from the limited data available at the time, suggested that the open water surface was losing somewhere in the range of 150 to 200 watts per square metre to the atmosphere during winter, a rate comparable to what you might find in much warmer ocean regions. Over an area of 250,000 square kilometres, that adds up to an enormous amount of energy being transferred from the ocean interior to the atmosphere. The Polynya is not a passive feature. It is an active heat engine, running on the thermal energy stored in the deep water below. What makes this particularly interesting is the self-sustaining nature of the process. Once deep convection begins, it modifies the water column in ways that tend to perpetuate it. The mixing erodes the stratification further, making it easier for warm water to continue rising. The open water surface changes the local atmospheric conditions. The temperature difference between the water and the surrounding ice creates circulation patterns that can drive additional mixing at the surface. The system develops a kind of momentum. It is not simply that the warm water comes up and melts some ice. It is that the act of coming up changes the conditions in a way that makes it easier for more warm water to come up. The Polynya, once established, works to maintain itself. This is also why the Polynya can persist through an entire winter, even when the air temperatures above it are cold enough to freeze seawater in minutes. The convective heat supply from below is continuously replenished by the circulation of the Weddell Gyre, which draws more circumpolar deep water into the region. As long as the convection is running and the gyre is supplying warm water from depth, the surface stays open. The cold air above cannot win against the heat coming from below, because the ocean's interior is a much larger reservoir of energy than the thin layer of atmosphere directly above it. The salinity of the water column plays a critical role in all of this, and it is worth spending a moment on that because it is easy to underestimate how much salt matters in ocean physics. Salinity affects the density of water in the same direction as temperature, but through a different mechanism. Cold water is denser than warm water. Salty water is denser than fresh water. The surface layer in the Weddell Sea is kept light, and therefore stable as a lid, partly by its coldness and partly by its relative freshness. If that layer becomes saltier, its density increases, the stability of the stratification decreases, and the system moves closer to the threshold where convection can begin. Small changes in salinity can have significant effects on whether the lid holds or breaks. This is one reason why events at the surface, storms, changes in ice formation rates, shifts in precipitation, can have consequences that reach all the way down into the deep water. When sea ice forms, it does not incorporate much salt. The salt is expelled into the surrounding water, a process called brine rejection. This makes the surface water saltier and denser, which erodes the freshwater lid from below. Conversely, when ice melts, it releases fresh water, which freshens the surface layer and strengthens the lid. The balance between ice formation and ice melt, between precipitation and evaporation, between storm-driven mixing and calm conditions, all of these affect the salinity of the surface layer and therefore the stability of the stratification. In the vicinity of moored rise, as the previous section established, the Taylor column effect tends to concentrate water with particular properties, including water that is already somewhat less stratified than the surrounding ocean. The seamount creates a preferred location where the lid is thinner, where the gap between the surface layer and the circumpolar deep water below is smaller, where the threshold for convection is easier to cross. But the seamount does not cause the convection by itself. It identifies the location where convection is most likely to begin. The actual trigger, the thing that finally pushes the system over the edge, is typically something happening at or near the surface. In the 2016 and 2017 events, which provided the most detailed observational data available, researchers found evidence that intense storms over the Southern Ocean had played a significant role in initiating the convection. Southern Ocean storms are not gentle. They can generate winds of considerable force, driving waves and mixing energy down into the upper ocean. When a major storm passes over the Weddell Sea, it can mix the surface layer vigorously, eroding the stratification that normally keeps the warm water below sealed off. If the stratification is already weakened, if the lid is already thin, perhaps because of a period of stronger ice formation and brine rejection, or a shift in the local salinity balance, then a sufficiently intense storm can push the system past the threshold. The warm water below begins to rise, the convection starts, and once it starts, the self-reinforcing nature of the process takes over. There is something almost counterintuitive about this. A storm, which you might intuitively associate with cold and harsh conditions that would encourage ice formation, can actually be the thing that opens a hole in the ice, not by warming the surface directly, but by disrupting the stratification that was protecting the surface from the warmth below. The storm does the mixing, the ocean's own stored heat does the rest. This also begins to answer the question of why the Polynya does not appear every stormy year. Storms are common over the Southern Ocean, and it is one of the windiest and most turbulent ocean regions on Earth. But a storm alone is not sufficient. The stratification has to be weak enough beforehand that the storm's mixing energy can push the system over the threshold. If the surface layer is thick and fresh and well stratified, even a powerful storm may not be enough to initiate deep convection. The storm mixes the surface, but the warm water below remains too far down to reach. The conditions have to be preconditioned. The stratification has to be eroded over time by slower processes. The salinity of the surface layer has to be nudged upward by brine rejection or reduced freshwater input. The circumpolar deep water below has to be close enough to the surface that only a modest additional push is needed. When all of those slower processes have moved the system close enough to the threshold, a storm can provide the final push. When they have not, the storm passes and the ice remains intact. This is a picture of the Polynya as something that emerges from the interaction of processes operating on very different timescales. The shape of moored rise is essentially permanent on any human timescale. The Weddell Gyre oscillates on timescales of years to decades. The stratification of the water column changes on timescales of months to years, driven by ice formation, melting, precipitation, and the slow circulation of the gyre. And the storms that can trigger the final convective event operate on timescales of days. The Polynya is the result of all of these timescales converging, the slow preconditioning bringing the system to the edge, and the fast trigger pushing it over. It is a genuinely elegant piece of ocean physics once you see it whole. Not elegant in the sense of being simple. The actual mathematics of convective instability in a rotating stratified fluid are not simple at all, but elegant in the sense that the pieces fit together into a coherent picture. The seamount concentrates the vulnerability. The gyre supplies the heat from depth. These slow changes in stratification bring the system to the threshold. The storm provides the trigger. The convection becomes self-sustaining. The Polynya opens and holds itself open against the winter cold. What this picture also makes clear is that the Weddell Polynya is not, in any meaningful sense, a random event. It is a structured response to a specific set of conditions. It keeps returning to roughly the same location because moored rise is always there, concentrating the conditions that make convection most likely. It appears intermittently rather than continuously because the preconditioning, the slow erosion of the stratification, takes time, and the conditions do not always align. And when it does appear, it runs on the ocean's own stored heat, maintaining itself through the same convective process that triggered it. But understanding the mechanism in physical terms is one thing. Actually observing it, gathering measurements of what is happening in the water column during an active Polynya event, tracking the temperatures and salinities at different depths, watching the convection develop in real time, is something else entirely. For most of the period between the 1970s and the 2010s, the Weddell Polynya was understood largely in theoretical terms, because the direct observational data simply did not exist. The Polynya had not reappeared at large scale, and the Weddell Sea itself made direct observation extraordinarily difficult under any conditions. That gap between theory and observation, between what the physics suggested was happening and what researchers could actually measure, is the next part of this story. So the Polynya closed in 1977. The satellite data stopped showing that dark window of open water. The ice moved back in, the Weddell Sea sealed itself over, and from the outside it looked as though nothing unusual had ever happened there. For scientists who had spent the late 1970s trying to make sense of what the Nimbus 5 data was showing them, this was a strange kind of ending. The phenomenon they had been trying to explain had simply stopped, not because they had found an answer, but because the Polynya itself had decided, in the way that ocean processes decide things, that conditions were no longer right. The years that followed were quiet in the Weddell Sea, at least by the measure of large open water events. Researchers continued working on the theoretical side of things, the ocean physics, the convection models, the role of moored rise, but without an active Polynya to observe, they were largely working from the 3 years of satellite data they already had, and from what could be inferred about the water column from limited ship-based measurements. The Weddell Sea is not an easy place to reach at the best of times, and in winter, when the Polynya had formed, it was essentially inaccessible to research vessels. So the window had closed in more than one sense. Through the 1980s and into the 1990s, some researchers began to wonder whether the 1974 to 1976 event might have been genuinely anomalous. A one-time alignment of conditions that had briefly produced something extraordinary and then resolved itself back into normal ocean behaviour. This was not an unreasonable position. The Polynya was large enough and strange enough, and the conditions required to produce it seemed specific enough, that a single occurrence over the span of the satellite record was not obviously inconsistent with it being rare or even unique. Without seeing it again, there was no way to know whether it was a recurring feature of the Weddell Sea or something that had happened once and might not happen again for centuries. That uncertainty sat in the literature for a long time. Papers continued to be written about the mechanism, about what the 1970s data implied about deep ocean convection, about the role of the Weddell Gyre and the geometry of moored rises. The theoretical picture was developing, but the observational foundation remained thin, and there was a particular frustration built into the situation that any researcher who has worked on intermittent natural phenomena will recognise. You cannot design a field campaign around something that does not exist. You cannot send a ship to observe a Polynya that is not there. You can only prepare as best you can and wait. Then, in 2000 and again in 2001, something happened. Not on the scale of the 1970s event, nothing close to the 250,000 square kilometres that the Nimbus 5 data had shown at the Polynya's peak, but a notable smaller opening appeared in the sea ice near moored rise. The area involved was modest by comparison, but the location was essentially the same. Right there, above that seamount, the ice had thinned and opened in a way that was consistent with the same general mechanism. Some researchers found this genuinely encouraging. It suggested that the 1970s event had not been a complete one-off, that the conditions near moored rise could occasionally produce some version of this phenomenon, even if the full-scale Polynya had not returned. Others were more cautious, noting that a small coastal adjacent opening was quite different from the vast open ocean feature that had appeared in the 1970s. The 2000 and 2001 events were interesting data points, but they were not the Polynya coming back. They were more like a reminder that the potential was still there. Studying the Weddell Sea during this period required a certain kind of ingenuity, because the traditional tools of oceanography, research ships, lowered instruments, water samples collected at depth, were largely unavailable for the region during winter. You cannot send a ship into pack ice several metres thick in the middle of the Antarctic winter without extraordinary risk and extraordinary cost. The few expeditions that did operate in the Weddell Sea during this period were summer operations, when the ice retreated enough to allow access to parts of the basin. They gathered valuable data, but they were not observing the conditions that produced the Polynya. They were arriving after the winter had passed, looking at what remained. Two technologies changed this situation significantly, though neither of them was designed specifically with the Weddell Polynya in mind. The first was the Argo float program. Argo is a global network of autonomous profiling floats, small, roughly metre-long instruments that drift freely through the ocean, periodically diving to depths of around 2,000 metres, measuring temperature and salinity as they rise back to the surface, then transmitting their data via satellite before diving again. The program began expanding significantly in the early 2000s, and by the mid-2000s there were thousands of Argo floats operating across the world's oceans, including the Southern Ocean. For the Weddell Sea specifically, Argo floats offered something that ship-based measurements could not: year-round data from a region that was effectively closed to direct human access in winter. A float does not care about sea ice or wind chill or the darkness of the Antarctic winter. It just drifts and dives and transmits. The limitation of standard Argo floats in the Weddell Sea was for a long time the ice itself. When a float surfaces beneath sea ice, it cannot transmit its data, and it risks being damaged or destroyed. Modified ice-capable floats were developed to address this, able to detect ice cover and delay their surfacing until they found open water. These instruments extended the reach of the Argo network into the most ice-covered parts of the Southern Ocean, including the regions where the Polynya had appeared in the 1970s. Slowly, year by year, a subsurface picture of the Weddell Sea began to accumulate. Temperature profiles, salinity profiles, the structure of the water column across different seasons and different years. The second technology was stranger and, in its way, more poetic. Researchers began attaching sensors to elephant seals, not in a harmful way. The instruments were glued to the fur on the seals' heads and shed naturally when the animals molted. But while the seals were at sea, diving repeatedly in search of food, they were also collecting oceanographic data: temperature, salinity, depth. The same measurements that an Argo float would take, but from an animal that navigated the Weddell Sea with a competence that no human instrument could match. Elephant seals dive deep, they range widely, and they are entirely indifferent to the conditions that make the Weddell Sea inhospitable to human researchers. They go where the fish are, which means they go where the ocean is, which means they go places that instruments cannot easily reach. This program, eventually formalized as MEOP, the marine mammals exploring the oceans pole to pole, provided data from under the sea ice that would have been essentially impossible to collect any other way. Seal-mounted sensors contributed measurements from the deep Weddell Basin during winter months, filling in parts of the picture that had been blank for decades. The idea of using animals as oceanographic platforms has a slightly absurdist quality to it. There is something gently amusing about the notion that our understanding of one of the most important ocean features on Earth depends in part on the dietary habits of large marine mammals, but the data were real and the contribution was significant. By the early 2010s, researchers had a much richer picture of the Weddell Sea's subsurface structure than they had possessed at any previous point. What this data was showing, gradually, was that the water column in the Weddell Sea near Maud Rise was not static between the major Polynya events. The stratification, the layering between the cold, fresh surface water and the warmer, saltier water below, varied from year to year in ways that seemed to track with broader changes in the Southern Ocean. Some years the stratification was stronger, the lid thicker and more resistant to disruption. Other years it appeared weaker, the temperature and salinity contrast between layers less pronounced, the warm, deep water sitting closer to the surface. The system was not simply waiting passively for the next event, it was fluctuating, breathing in a slow ocean rhythm, sometimes approaching the conditions that had produced the 1970s Polynya, and sometimes moving away from them. This was useful information, but it was also somewhat tantalizing. Researchers could see the stratification varying. They could see in some years that the conditions near Maud Rise looked more vulnerable than in others. But without an active Polynya to observe, they could not be certain which combination of factors would actually push the system over the threshold. The theory said that weakened stratification, combined with the right storm at the right time, could trigger deep convection. The data suggested that the stratification was indeed weakening in some periods, but the Polynya itself was not cooperating. It was not returning. There is a particular kind of scientific patience required in this situation. You have a phenomenon that appeared for 3 years, then vanished. You have a theory that explains it reasonably well. You have data suggesting the conditions are sometimes close to favourable, and you wait. You publish papers about the mechanism, you refine the models, you add more floats to the Southern Ocean, you tag more seals, you watch the satellite data every Antarctic winter for the signature of open water, where there should be ice. And mostly, year after year, the Weddell Sea stays frozen and gives nothing away. It is worth saying plainly that the gap in direct observation had real consequences for how well the Polynya was understood. The theoretical models were developed largely without the constraint of detailed subsurface measurements from an active event. Researchers could model what they thought was happening in the water column during a Polynya, but they could not verify those models against real data from the real thing. This is not unusual in oceanography. The ocean is large and expensive and dangerous to study, and there are many important processes that are understood primarily through theory and limited observation. But it does mean that the confidence intervals around any specific claim about the Polynya mechanism were wider than scientists would have liked. The broad picture seemed right. The details were uncertain. The seal data and the Argo floats helped. The summer ship expeditions helped. The improving satellite coverage helped. But there was no substitute for observing the Polynya itself in real time, with instruments in the water column while the convection was actually happening. That opportunity had not come since 1977. It was now the 2010s. Nearly 4 decades had passed. And then, in September 2016, the satellite images from the Weddell Sea showed something that researchers had been waiting a very long time to see. A hole in the ice, not as large as the 1970s event, nowhere near 250,000 square kilometres, but roughly 33,000 square kilometres of open water, sitting above Maud Rise, in the middle of the Antarctic winter. The Polynya had not fully returned yet, but it was opening. The system was moving. Something was happening in the water column beneath that patch of dark open ocean, and this time, for the first time since the Nimbus 5 data of the 1970s, there were instruments nearby that could actually see what it was. The 33,000 square kilometres of open water that appeared in September 2016 was, by any reasonable measure, a significant event. To put that in physical terms, it was roughly the size of Belgium, or the state of Maine, sitting open and dark in the middle of a sea that should have been locked under winter ice. For most of the world, this went unnoticed. It was a patch of ocean in one of the most remote places on Earth, during a season when almost no one was anywhere nearby to observe it. But for the small community of researchers who had been watching the Weddell Sea for years, some of them for their entire careers, it was the kind of thing you send an email about at whatever hour you happen to be awake. The 2016 opening was notable, but it was also somewhat ambiguous. Smaller openings had appeared near Maud Rise before, in 2000 and 2001, without developing into anything close to the scale of the 1970s event. There was no guarantee that what was happening in September 2016 would be different. It might open, persist for a few weeks, and close again without revealing much. The instruments in the region, primarily SOCOM floats, part of the Southern Ocean Carbon and Climate Observations and Modelling Project, were gathering data, but it was not yet clear what story that data would tell. Researchers were watching carefully, with the kind of measured excitement that comes from long experience with phenomena that do not always cooperate with expectations. SOCOM is worth pausing on for a moment, because it represents exactly the kind of infrastructure investment that makes modern oceanography possible, in a way it simply was not in the 1970s. The project, funded largely by the National Science Foundation and involving institutions across the United States, deployed a network of autonomous profiling floats across the Southern Ocean, floats equipped not just with the standard temperature and salinity sensors, but also with biogeochemical sensors capable of measuring oxygen, nitrate, pH, and other properties relevant to carbon cycling. These floats dive to around 2,000 meters, drift for about 10 days, then rise slowly to the surface while collecting a full vertical profile of the water column, transmitting their data by satellite before descending again. They do this continuously in all seasons, in conditions that would make crude observation essentially impossible. By 2016, there were enough of them in the Weddell Sea region to provide meaningful coverage of the area around Maud Rise. When the Polynya opened, some of those floats were positioned to drift beneath it, or close enough to capture what was happening in the water column nearby. What the SOCOM floats began to show was striking. The water column beneath the 2016 opening was weakly stratified in a way that matched what the theory had predicted would be necessary for deep convection to occur. The cold, fresh surface layer, the lid that normally keeps the warm, deep water from reaching the surface, was thinner than usual and less stable. The warm, salty, circumpolar deep water below was sitting relatively close to the surface, not by dramatic amounts, but close enough that any additional mixing could potentially allow it to break through. The floats were not just confirming that the Polynya existed, they were providing for the first time a real-time subsurface portrait of the conditions that produced it. Then September 2017 arrived, and the Polynya returned on a completely different scale. The 2017 opening was approximately 80,000 square kilometres at its peak, more than twice the size of the 2016 event, and large enough to attract attention well beyond the oceanographic community. News outlets reported on it. Science journalists wrote explainers. The image of a vast dark hole surrounded by white Antarctic sea ice, captured in satellite photographs and shared widely, was striking enough to register with people who had never previously thought about the Weddell Sea. 80,000 square kilometres is roughly the size of Scotland, or the state of South Carolina. It is not a small thing. It is the kind of feature that is visible from space in a way that is immediately legible even to someone with no background in polar oceanography. The University of Southampton's researchers were among those who commented publicly on the event, as were scientists associated with SOCOM and a number of other institutions. The tone was one of cautious scientific excitement. This was a genuine opportunity, the first time since the 1970s that a large-scale Weddell Polynya had opened while modern observational infrastructure was in place to study it. Researchers were careful not to overclaim. The 2017 event was large, but it was not the size of the 1974 to 1976 events. The mechanisms were not yet fully confirmed. There were still significant questions about what exactly had triggered the opening, and why it had expanded so dramatically from 2016 to 2017. But the data being collected was real, it was detailed, and it was going to be analysed for years. One of the things that made the 2017 event particularly useful was that researchers could now compare the conditions inside the Polynya, the water column properties beneath the open water, with conditions in the surrounding ice-covered areas. The SOCOM floats provided profiles from both regions, and the contrast was informative. Inside the Polynya, the water column showed signs of active deep convection. Relatively uniform temperature and salinity from near the surface down to several hundred meters, consistent with the kind of vigorous vertical mixing that the theory predicted. Outside the Polynya, the normal stratification was intact. The boundary between these two regimes was surprisingly sharp in some of the float profiles, which gave researchers a clearer picture of how localized and self-contained the convection process was once it got started. The question of what had changed between 1977 and 2016 was one that researchers found genuinely difficult to answer with certainty. Several factors seemed to be involved, and they were not easy to disentangle. One observation was that the Weddell Gyre had strengthened somewhat over the intervening decades, which would have intensified the upwelling of warm, deep water near Maud Rise and potentially made the stratification there more vulnerable to disruption. Another was that Southern Ocean salinity patterns had shifted, The surface water in parts of the Weddell Sea had become slightly saltier in recent years compared to earlier decades, which would reduce the stability of the cold, fresh lid and make convection easier to trigger. Saltier surface water is denser, and denser surface water is more easily displaced by the warm water rising from below. There was also the question of storms. The Southern Ocean is one of the stormiest regions on Earth, and the intensity and frequency of Southern Ocean cyclones had been the subject of considerable research. In the period leading up to the 2016 and 2017 openings, the Weddell Sea region had experienced several intense storm events that would have mixed the surface layer and eroded the stratification near moored rise. The storms alone would not have been sufficient to trigger the Polynya. The subsurface conditions had to be right first. But given a water column that was already weakly stratified, and a moored rise that was already creating its characteristic upwelling effect, a sufficiently powerful storm could provide the final push that allowed the warm, deep water to break through. This combination, weakened stratification, intensified gyre upwelling, and storm-driven surface mixing, appeared in the published research that followed the 2016 and 2017 events. Papers in journals including Nature and the Journal of Geophysical Research, published around 2019, work through the observational data and the model results in careful detail. The authors were clear about what the data supported and what remained uncertain. The deep convection model was confirmed as the primary mechanism. The role of storms as a triggering factor was supported by the timing of the openings relative to storm activity in the region. The moored rise connection was reinforced, but the exact threshold conditions, precisely how weak the stratification needed to be, precisely how strong the storm needed to be, remained difficult to pin down with the data available. There is something worth sitting with here, which is the sheer span of time involved. The 1970s event lasted 3 years and then disappeared. Researchers spent nearly 4 decades building theory, deploying instruments, tagging seals, running models, and waiting. And then the Polynya returned, and within 2 years there were published papers in major journals drawing on real-time subsurface data. The speed of the scientific response in 2016 and 2017 was a direct result of all that preparation during the quiet years. The Argo floats were already in the water, the SOCOM network was already deployed, the satellite coverage was already in place. When the Polynya opened, the instruments were there. That does not happen by accident. It happens because a small number of researchers spent a long time getting ready for something that most of them were not certain they would live to see return. The media attention that came with the 2017 event was in some ways a mixed experience for the scientists involved. On one hand, public interest in the Weddell Polynya meant more awareness of Southern Ocean research, which is genuinely underfunded relative to its importance. On the other hand, some of the coverage treated the Polynya as more mysterious and alarming than the researchers themselves felt was warranted. Headlines used words like massive and mysterious hole in ways that implied something more dramatic than what was actually happening, which was, in essence, a well-understood physical process operating at a scale that had not been observed in 4 decades. The Polynya was scientifically important and genuinely interesting. It was not a catastrophe, and it was not inexplicable. Researchers found themselves doing a fair amount of careful public communication, explaining what the Polynya was and what it was not, and gently correcting the more alarming interpretations that circulated online. What the 2016 and 2017 events did not fully resolve was the question of why the Polynya had returned specifically at this point in time, rather than at some other point in the past 40 years. The conditions that seemed to favour the opening, weakened stratification, a strengthened gyre, storm activity, were not unique to 2016. Some of those conditions had been present in other years without producing a large opening. This suggested that the triggering mechanism was more sensitive and more contingent than the broad description implied. It was not enough for the stratification to be weakened. It had to be weakened to the right degree, in the right location, at the right time relative to storm activity and the specific configuration of the gyre. The system had multiple conditions that all needed to align, and they aligned imperfectly and infrequently. which is, in a sense, why the Polynya is rare. There was also a forward-looking dimension to the 2016 and 2017 data that researchers were already beginning to think about. If the conditions that allowed the Polynya to return were partly connected to broader changes in the Southern Ocean, warming deep water, shifting salinity, changes in storm patterns, then the 2016 and 2017 events might not be an isolated return after a long absence. They might be the beginning of a new phase of activity, or they might be an isolated cluster within a longer quiet period. Without more events to compare, it was genuinely difficult to say. The sample size of major Weddell Polynya events remained very small. The 1970s cluster, the minor 2000 and 2001 openings, and now the 2016 and 2017 events. Drawing firm conclusions from a dataset that's small requires more caution than the situation comfortably allows. What the 2017 event made clear, above all else, was that the Polynya was not simply a historical anomaly. It was a recurring feature of the Weddell Sea, recurring on a timescale that is long relative to a human research career, but short relative to the timescales on which the ocean normally operates. It had come back once. It would, in all likelihood, come back again. The question of when and under what conditions and what it would look like when it did was now a live research question in a way it had not quite been before. The instruments were in place, the models were better calibrated. The researchers who had spent years preparing for this moment now had real data to work with, and they were already thinking carefully about what that data revealed, about the specific mechanism that allowed the Polynya to form and persist, a mechanism in which one particular underwater mountain, rising silently from the floor of the Weddell Sea, plays a role that is considerably more central than its quiet, submerged existence might suggest. That underwater mountain is Maud Rees, and it sits at roughly 65 degrees south, 3 degrees east, rising about 3,000 metres from the floor of the Weddell Sea. From the surface, you would never know it was there. The water above it looks the same as the water anywhere else in that part of the ocean. Dark, cold, heavy with ice in winter. But beneath the surface, Maud Rise is doing something that no flat stretch of seafloor could do. It is shaping the water that flows over it in a way that makes the Polynya not just possible, but almost predictable in its location, even if the timing remains elusive. To understand what Maud Rise actually does, it helps to think about what happens when a large, slow-moving body of water encounters a tall obstacle on the ocean floor. The water cannot simply flow over it the way a river flows over a submerged rock, because the ocean is rotating. The Earth's rotation imposes a constraint on how fluid moves at these latitudes. The Coriolis effect, which deflects moving water to the left in the southern hemisphere, interacts with the seamount's topography to create something called a Taylor column. It is a somewhat counterintuitive piece of fluid dynamics, and it was described theoretically long before oceanographers had any reason to connect it to the Weddell Sea. The basic idea is this: when a rotating fluid flows over a tall, steep obstacle, the fluid directly above the obstacle cannot easily move across it. Instead, it tends to stay put, forming a column of water that rotates in place above the seamount, isolated from the surrounding flow. Think of it less like water flowing over a hill, and more like water flowing around a spinning top that happens to be fixed to the sea floor. The column above the seamount becomes a kind of eddy, trapping and recirculating the water within it rather than letting it mix freely with the broader ocean. This is a Taylor column, and Maud Rise generates one. Now, what makes this relevant to the Polynya is what gets trapped inside that column. The water directly above Maud Rise tends to have slightly different properties than the water around it, and specifically, it tends to be more weakly stratified. The normal Southern Ocean structure, as described earlier, has a cold, fresh surface layer sitting on top of warmer, saltier water below. The Taylor column above Maud Rise disrupts this arrangement. The rotating column brings water from different depths into contact with each other, gently eroding the density difference between the surface layer and the warm layer beneath it. Over time, the stratification above moored rise becomes thinner and more fragile than it is in the surrounding ocean. This is the key. The Polynya does not form randomly somewhere in the Weddell Sea. It forms above moored rise because that is where the stratification is most vulnerable. The seamount creates a preferred location, a weak point in the ocean's thermal armour, if you want to put it that way. When conditions are right for convection to begin, this is where it begins. The Taylor column concentrates the vulnerability. It is not the only factor, but it is the factor that explains the geography of the Polynya, the reason it keeps coming back to roughly the same coordinates rather than drifting across the basin. Researchers studying moored rise have found that the strength of the Taylor column effect is not constant. It varies depending on how strongly the Weddell gyre is flowing. The gyre is the large, slow, clockwise rotating current system that fills the Weddell Sea basin, and its strength fluctuates over years and decades in response to wind patterns, temperature gradients, and other large-scale climate signals. When the gyre is relatively strong, the flow of water past moored rise is more vigorous, and the Taylor column above the seamount is more pronounced. The water above the seamount is more effectively isolated. The stratification there is more thoroughly eroded, and the conditions for convection are more easily met. When the gyre is weaker, the Taylor column effect is less pronounced. The water above moored rise is less isolated. The stratification is maintained more effectively, and the Polynya is less likely to form even if other conditions, storm activity, deep water temperature, are roughly similar. This helps explain one of the questions that the 2016 and 2017 data raised. Why do some years with strong storms and warm deep water still fail to produce a large Polynya, while other years succeed? Part of the answer may lie in the gyre. The gyre needs to be strong enough to produce a well-developed Taylor column, which requires the stratification above moored rise to be sufficiently weakened before the storms can do their work of triggering the actual convection. It is a cascade of conditions, not a single switch. The gyre sets up the vulnerability. The Taylor column concentrates it in one place. The storms provide the final perturbation that tips the weakened stratification over into full convection. Remove any one of those elements and the Polynya may not form, even if the others are present. This is why the phenomenon is rare and irregular rather than appearing on a neat schedule. The ocean has to arrange several different things at once, and it does not do so on any timetable that is easy to predict from the outside. What is interesting about this picture is that it gives researchers a set of observable preconditions to monitor. If you can track the strength of the Weddell gyre, the state of stratification above moored rise, the temperature of the circumpolar deep water, and the frequency and intensity of Southern Ocean storms, you have at least a partial set of indicators that might give some warning before the next major Polynya event. You would not necessarily know years in advance, but you might know months in advance that conditions were becoming favourable. This is one of the practical goals of the ongoing monitoring programs in the Weddell Sea, not just to understand past events, but to develop enough situational awareness to catch the next one early. The SOCOM floats that provided so much of the subsurface data during the 2016 and 2017 events were part of this broader effort. They were not deployed specifically in anticipation of a Polynya. They were part of a general program to monitor the Southern Ocean's carbon and heat content. But their presence above and around moored rise during the active years turned out to be extraordinarily useful. The float data showed, in real time, how the water column above the seamount was changing as the Polynya developed. Researchers could see the stratification weakening, the warm deep water rising, the convective mixing intensifying. It was the first time this sequence had been observed directly from below, rather than inferred from surface imagery. What those measurements confirmed, in granular detail, was that the water column above moored rise during the 2016 and 2017 events was unusually weakly stratified compared to surrounding areas and compared to historical norms. The cold, fresh surface layer was thinner than usual, in some locations barely present at all. This was not solely the result of storm mixing, though storms had contributed. It also reflected a longer-term trend in the region. the surface layer above moored rise had been gradually losing some of its freshness, becoming slightly saltier than it had been in earlier decades. Saltier water is denser, which means it sinks more readily, and is harder to maintain as a stable lid over the warmer water below. The source of this salinity change is itself an active area of research. One possibility is that changes in sea ice production around the Weddell Sea had altered how much fresh water was being added to the surface layer in that region. Sea ice formation actually increases salinity. When water freezes, the salt is expelled into the surrounding ocean, making it denser. If ice formation patterns shifted in ways that concentrated this brine rejection above moored rise, it could have gradually eroded the freshness of the surface layer there over years. Another possibility involves changes in precipitation and in the transport of fresh water from melting ice sheets elsewhere. The Southern Ocean's freshwater budget is complicated, and different parts of it are changing at different rates. What makes moored rise specifically interesting in this context is that the Taylor column above it acts as a kind of collector. It tends to trap and concentrate whatever properties the water above it has, including salinity anomalies. If the broader region becomes slightly saltier at the surface, the Taylor column may amplify that signal locally, making the stratification above moored rise weaker than it would be in the surrounding ocean. This seamount does not just create a preferred location for the Polynya, it may also act as an amplifier of the conditions that make the Polynya possible. Small regional changes in salinity or temperature, which might not be enough to trigger convection over a flat sea floor, might be enough when they are concentrated and intensified by the Taylor column dynamics above moored rise. This is admittedly still partly theoretical. The observational record above moored rise is sparse compared to what researchers would ideally have. The seamount sits in one of the least visited parts of the ocean, and continuous monitoring of the water column there across all seasons and years is simply not yet possible with the instruments currently deployed. The SOCOM floats drift through the area rather than staying fixed above it. Their data is valuable but not comprehensive. Researchers are working with a partial picture and they know it. There is also the question of how the Taylor column itself varies on longer timescales. The Weddell Gyre's strength is not constant, and neither is the precise structure of the flow past moored rise. In some years, the seamount may generate a well-defined, stable Taylor column. In other years, the flow may be less organised, the column less coherent, and the concentrating effect on stratification less pronounced. Tracking these variations requires sustained observations that simply do not yet exist in sufficient density. Some of what researchers know about the gyre's variability comes from satellite altimetry, measurements of the sea surface height, which reflects the speed and direction of ocean currents below. But translating sea surface height into a precise picture of what is happening 3,000 meters down, above a specific seamount, involves significant inference. Despite these gaps, the picture that has emerged from the combination of float data, satellite observations and modelling work is considerably clearer than it was before 2016. Moored rise is not just a passive geographic feature that happens to sit beneath the Polynya. It is an active participant in the process, shaping the water above it in ways that make convection more likely there than anywhere else in the Weddell Sea. The Taylor column it generates is sensitive to the gyre's strength, which varies on multi-year to decadal timescales. The stratification it helps to erode is sensitive to regional salinity trends, which are themselves connected to larger patterns of sea ice formation and freshwater input. And the convection it helps to trigger, once it begins, is self-reinforcing. Warm water rises, melts ice, exposes dark ocean surface, which absorbs heat, which warms the water further, which drives more convection. The seamount, in this sense, is the keystone of the whole system. It is the reason the Polynya has a home. Without moored rise, the conditions that produce the Weddell Polynya might still exist in the Weddell Sea. The warm deep water, the weakened stratification, the storms, but they would have no particular place to concentrate. The Polynya might still form occasionally, but it would be more diffuse, more variable in location, harder to study and harder to predict. Moored rise gives the system a fixed point, a recurring address, a place where the ocean's internal tensions are most likely to break through to the surface. It is a somewhat strange thing to think about, that a mountain on the seafloor, completely invisible and completely unreachable under normal circumstances, is quietly organising one of the more unusual features of the global ocean. Maud Rise was named after the Norwegian ship Maud, which attempted to navigate the Northeast Passage in the 1920s and eventually became trapped in Arctic ice. There is a certain irony in the name, a ship defeated by ice, lending its name to a seamount that keeps punching holes in ice. The ocean has a long memory and a dry sense of humour. What the Maud Rise story adds to the broader picture of the Weddell Polynya is a sense of mechanism that is both elegant and genuinely complex. It is not one thing. It is a chain of interacting processes, each of which is individually understandable, but which combine in ways that are sensitive to conditions that vary independently of each other. Understanding the seamount's role does not make the Polynya predictable. It makes it more legible, which is a different and in some ways more useful thing. And what that legibility reveals, when you follow it outward from the seafloor to the surface and then upward into the atmosphere, is that the Polynya's effects do not stay contained in the Weddell Sea. They reach considerably further than the dark patch of open water visible from a satellite image would suggest. So when you follow the effects of the Polynya upward from the seafloor, from Maud Rise's summit, through the convecting water column, past the vanishing ice, you eventually reach the surface, and the surface is where the Polynya becomes visible to the rest of the world, not just as satellites, but to the atmosphere itself. But before getting there, it is worth staying with Maud Rise a little longer, because the seamount's role in the story is not quite finished. What the Taylor column does is concentrate and organise. That much has been established. But the specific way it does this, and why that makes the seamount such a reliable trigger point rather than just a geographic curiosity, involves a piece of fluid dynamics that is genuinely strange when you first encounter it. Taylor columns are named after Geoffrey Ingram Taylor, a British mathematician and physicist who described the phenomenon in the early 20th century. The basic idea is this: when a rotating fluid flows over an obstacle, a bump, a ridge, a seamount, the rotation of the fluid tends to resist vertical motion. The Coriolis effect, which is the same force that makes storms spin in different directions in the northern and southern hemispheres, acts on the fluid above the obstacle in a way that traps some of it. Instead of flowing smoothly over the seamount and continuing on its way, a portion of the water above the peak gets caught in a slow, persistent rotation. It becomes, in effect, a column of water that behaves differently from its surroundings, spinning gently, relatively isolated from the flow around it, and accumulating whatever properties the water there happens to have. Above Maud Rise, the seamount rises roughly 3,000 metres from the seafloor. Its peak sits at around 1,600 metres below the surface, which is still deep, but deep enough that the water column above it is considerably shallower than in the surrounding basin. That shallower water column, combined with the Coriolis effect and the rotation of the Weddell Gaia, produces a Taylor column that researchers have been able to detect through measurements of sea surface height and current patterns. The column is not always perfectly formed. It varies with the strength and direction of the gyre flow, but in conditions where the gyre is strong and well organised, the Taylor column above Maud Rise is a persistent feature. What this means practically is that the water sitting above the seamount is to some extent cut off from the broader mixing and exchange happening in the surrounding Weddell Sea. It sits there, turning slowly, accumulating, and crucially, if the stratification in that column becomes weakened, if the cold fresh surface layer becomes thinner or saltier than usual, the Taylor column concentrates that weakness. It does not let it diffuse away into the surrounding ocean. It holds it in place above the seamount until conditions are right for convection to begin. This is what makes Maud Rise a trigger point rather than just a location. In a flat-bottomed ocean, a regional weakening of stratification would spread out, dilute, and perhaps never reach the threshold needed to start deep convection. Above moored rise, that same weakening gets focused. The threshold gets crossed locally, even when the broader ocean around it has not yet reached that point. The seamount, in this sense, is a concentrator of vulnerability. It takes a diffuse regional signal and turns it into a specific, localized event. Researchers studying the Taylor column above moored rise have found that its behavior is sensitive to the strength of the Weddell gyre in ways that help explain some of the Polynya's variability. When the gyre is stronger, flowing faster, more organized, the Taylor column is better defined and more effective at trapping water above the seamount. When the gyre weakens, the column becomes less coherent and the concentrating effect is reduced. This gyre variability operates on timescales of years to decades, which is part of why the Polynya does not appear every year. The seamount is always there. The warm, deep water is almost always present somewhere below. But the Taylor column's effectiveness and the stratification's vulnerability vary in ways that only occasionally align into the conditions needed for a full Polynya event. This also helps explain something that might otherwise seem puzzling: why smaller openings near moored rise, like those observed in 2000 and 2001, did not develop into the full-scale Polynya seen in the 1970s, or again in 2016 and 2017. In those years, the conditions were partially right. The Taylor column was doing its work, the stratification was somewhat weakened, and small patches of open water appeared above the seamount, but the alignment was not complete. The gyre may have been at an intermediate strength, the surface salinity may not have been quite anomalous enough, the storms may not have been intense enough to deliver the final push, the system got close but not close enough. The convection started briefly, and then the cold winter air won and the ice closed back over. It is a system with a threshold, in other words. Below the threshold you get nothing, or you get small transient openings. Above the threshold you get a self-reinforcing event that can sustain itself for months against the full force of an Antarctic winter. The seamount is not what sets the threshold. That is determined by the ocean's stratification and the heat content of the deep water. But it is what determines where the threshold is most likely to be crossed first. Some of the clearest evidence for the Taylor column's role came from the SOCM floats that were operating in the Weddell Sea during the 2016 and 2017 events. These autonomous instruments, drifting at depth and surfacing periodically to transmit data, happened to be in the right place at the right time. Floats that passed through the region above moored rise recorded distinctly different water column properties than those operating in the surrounding basin. The stratification was measurably weaker above the seamount. The temperature and salinity profiles showed signs of mixing that were not present elsewhere at the same depths. It was not just a theoretical prediction. The float data showed the Taylor column's fingerprint directly in the measurements. What the floats could not do, of course, was stay fixed above the seamount and watch continuously. They drift. They pass through and move on. So the picture they provided was a series of snapshots rather than a continuous record. And some of the most important moments, the exact timing of when deep convection began, how quickly it intensified, whether there were false starts before the main event, were not captured. The data was invaluable, but it was also incomplete in ways that researchers are still working around. There is also the question of how the Taylor column interacts with the storms that appear to play a role in triggering the convection. The 2016 and 2017 events were preceded by intense cyclonic storms over the Southern Ocean, and these storms mixed the surface layer in ways that eroded the stratification. But the storms did not target moored rise specifically. They were large-scale atmospheric events affecting broad areas of the Southern Ocean. The reason their effect was most pronounced above moored rise, researchers believe, is precisely because of the Taylor column. The storm's mixing was happening everywhere, but the Taylor column ensured that above the seamount, the already weakened stratification was pushed past the threshold. Elsewhere, the mixing was significant, but not quite enough. Above moored rise it was. This is a good example of how the Polynya is not caused by any single factor. The warm deep water is necessary but not sufficient. The weakened stratification is necessary but not sufficient. The storm-driven mixing is necessary but not sufficient. Moored rise and its Taylor column are necessary but not sufficient. It is the combination, the specific alignment of all these factors at once, in the same place, that produces the event. Remove any one of them, and the Polynya either does not form or forms much more weakly. This is partly why it is so hard to predict, and partly why it has remained puzzling for as long as it has. Researchers have also been looking at longer-term variations in the Weddell Gyre's strength as a possible explanation for the multi-decadal gap between the 1970s events and the return in 2016. Some studies using satellite altimetry and historical oceanographic data suggest that the gyre went through a period of relative weakness in the 1980s and 1990s, which would have reduced the Taylor column's effectiveness and made it harder for the Polynya to form, even when other conditions were partially favourable. Whether this gyre variability is itself connected to broader climate patterns, to changes in wind forcing over the Southern Ocean, or to shifts in the Antarctic circumpolar current, is still being worked out. The connections exist, but the causal chains are long and involve processes that are difficult to measure directly. There is a certain satisfaction in the moored rise story, if you step back from the complexity for a moment. The Polynya kept appearing in roughly the same location, decade after decade, and the reason turns out to be a mountain on the seafloor that nobody can see, generating a rotating column of water through the physics of a rotating planet. It is not an arbitrary coincidence of location. It is a consequence of geometry, rotation, and fluid dynamics working together in a specific and reproducible way. The seamount is not causing the Polynya in a simple sense. It is not generating the heat. It is not weakening the stratification on its own, but it is providing the address. It is the reason the Polynya has a home rather than wandering. Moored rise was first identified and named in the 1920s during the Norwegian expeditions of that era. For most of the 20th century, it was simply a feature on a bathymetric chart. A bump on the seafloor in an extremely remote part of the ocean, noted and catalogued but not particularly significant to anyone outside the small community of physical oceanographers. The connection between the seamount and the Polynya was not established until decades after the 1974 discovery, as researchers slowly assembled the pieces of the mechanism. There was no obvious reason, looking at a map, to suspect that a particular underwater mountain in the Weddell Sea was responsible for one of the most unusual ocean features on Earth. The understanding emerged gradually, through the accumulation of data and the development of better models. That gradual emergence is itself worth noting because it reflects something true about how oceanography works. The ocean is large and mostly inaccessible, and the processes that matter most in it often operate at depths and timescales that make direct observation extremely difficult. Understanding something like the Weddell Polynya requires putting together evidence from satellites, from instruments drifting at depth, from occasional ship expeditions, from computer models, and from theoretical fluid dynamics developed in entirely different contexts. No single observation explains it. No single researcher figured it out. It is a collaborative, incremental process that takes decades and still leaves significant gaps. The moored rise picture is now reasonably well established in its broad outlines. The Taylor column exists and concentrates stratification anomalies. The seamount creates a preferred location for convection. The gyre's strength modulates how effective the column is. Storms provide the triggering perturbation when other conditions are right. This is the consensus that has emerged from the work of the past decade, and particularly from the 2016 and 2017 observations. It is not the complete story. There are still details to be filled in, still variations to be explained, still questions about how all of this will behave as the climate continues to change. But the framework is solid enough that researchers now feel they understand, at least in principle, why the Polynya keeps coming back to the same place. And that understanding, once you have it, changes the way you think about the Polynya's effects, because if Maud Rheirs is the keystone, the fixed point around which the whole system organises, then the Polynya's consequences are not just local. The deep convection it drives, the water masses it produces, the atmospheric effects it generates above the open water surface, all of these radiate outward from that single point on the sea floor, influencing processes that extend far beyond the Weddell Sea. The seamount is, in a sense, the origin point of something much larger. And what happens when that open patch of dark water sits exposed to the Antarctic winter atmosphere? The heat it releases, the moisture it puts into the air, the deep water it sends sinking toward the global ocean floor is where the story opens up considerably. So let us think about what that open patch of water actually does. When the Weddell Polynya is active, you have a surface of dark ocean water sitting exposed in the middle of Antarctic winter. The air above it is extraordinarily cold, temperatures regularly falling below -20, -30 degrees Celsius. The surrounding sea ice reflects almost all of the sunlight that reaches it, but the open water absorbs it. More importantly, in winter there is almost no sunlight anyway. What matters most is not the light, but the heat exchange, and that exchange is dramatic. The open water is releasing enormous amounts of heat upward into the atmosphere, and the atmosphere is simultaneously pulling moisture off the surface and redistributing it as part of the broader storm systems that circle Antarctica continuously. Researchers have estimated that during an active Polynya event, the heat flux from the open water surface to the atmosphere can reach somewhere between 150 and 200 watts per square metre, and during intense events possibly higher. To put that in some kind of perspective, that is roughly comparable to the heat output you might expect from a moderately sunny day at temperate latitudes, except this is happening in the middle of Antarctic winter, surrounded by frozen ocean, in a place that would otherwise be releasing almost no heat at all. The contrast between the Polynya and the surrounding ice is not subtle, it is extreme. That temperature difference between the open water and the ice around it creates a strong pressure gradient in the lower atmosphere. Warm, moist air rises over the Polynya. Cold, dense air from the surrounding ice flows inward to replace it. This sets up a kind of persistent local circulation, not quite a storm, but a consistent atmospheric disturbance that sits above the open water for as long as the Polynya remains active. This local circulation interacts with the broader southern ocean weather systems, which are already among the most energetic on Earth. The Southern Ocean is famous for its storms, the roaring 40s, the furious 50s, the screaming 60s, as sailors used to call those latitudes. Introducing a persistent heat and moisture source in the middle of that environment does not go unnoticed by the atmosphere. The moisture that evaporates from the Polynya surface eventually gets carried into weather systems further north, contributing to precipitation patterns that are difficult to trace back to their source, but are real nonetheless. Some modelling work has suggested that active Polynya events in the Weddell Sea can influence the distribution of cloud cover and storm tracks across the broader southern hemisphere, though quantifying these effects precisely is genuinely difficult. The atmosphere and ocean are coupled in ways that make it hard to isolate the contribution of any single feature. But the basic physics is straightforward. A large open water surface in the middle of a frozen sea is a significant source of energy for the atmosphere above it, and that energy has to go somewhere. All of this, though, the local atmospheric effects, the heat flux, the storm interactions, is in some ways the smaller part of the story. The larger part happens below the surface, and it is connected to something that affects the entire planet. When the Polynya is open, the deep convection that sustains it is continuously producing water with very specific properties. The surface water, chilled by the brutal Antarctic atmosphere, becomes extremely cold. It also becomes saltier, because as sea ice forms at the edges of the Polynya, The ice crystals expel much of their salt content back into the surrounding water, a process called brine rejection. Cold and salty together means dense, and dense water sinks. The water produced by this process, cold, salty, dense, oxygen-rich from its time near the surface, sinks through the water column and eventually reaches the seafloor. From there, it spreads outward along the bottom of the ocean, flowing northward and eventually mixing into the deep basins of the Atlantic, Pacific and Indian Oceans. This is Antarctic bottom water, and it is one of the most important water masses on Earth. Antarctic bottom water is not a minor feature. It occupies the deepest layers of much of the world's ocean. When oceanographers take measurements in the deep Atlantic or the deep Pacific and find water that is extraordinarily cold and oxygen-rich sitting at the bottom, they are often looking at water that was last at the surface somewhere near Antarctica, possibly decades or even centuries earlier. The journey from the Weddell Sea to the deep North Atlantic takes a very long time. Some of this water will not see the surface again for hundreds of years. The reason this matters so much is that Antarctic bottom water is one of the main engines of the thermohaline circulation, the global system of deep ocean currents that is sometimes called the ocean conveyor belt. Though that name is a bit misleading in its simplicity, the thermohaline circulation is driven by density differences. Water that is cold and salty sinks, water that is warm and fresh rises, and between these two ends of the spectrum the ocean moves, slowly but continuously, carrying heat from the tropics toward the poles, carrying cold deep water from the poles toward the tropics, and in the process distributing energy, nutrients, oxygen and carbon across the entire planet. There are two main sites where deep water formation happens in the global ocean. One is in the North Atlantic, particularly in the Nordic seas and the Labrador Sea, where cold surface water sinks and feeds what is known as North Atlantic deep water. The other is around Antarctica, particularly in the Weddell Sea, where the processes we have been describing produce Antarctic bottom water. These two formation sites are the downwelling limbs of the global circulation, the places where surface water dives deep and begins its long journey through the ocean interior. The Weddell Polynya, when it is active, is directly contributing to one of these two critical formation sites. A large Polynya event significantly enhances the rate of Antarctic bottom water production in the Weddell Sea. And because this water eventually spreads to fill the deepest parts of the global ocean, a single Polynya event can have effects that persist for decades in the ocean interior, gradually influencing the temperature and oxygen content of water masses far from Antarctica. There is something genuinely striking about this when you think about it. A hole in the sea ice, forming in one of the most remote and inaccessible places on Earth, is participating in a process that connects to the deep ocean beneath the North Atlantic, beneath the Indian Ocean, beneath the tropical Pacific. The Weddell Sea is not isolated from the rest of the ocean. It is, in a sense, one of the places where the global ocean breathes, where surface properties are carried downward and spread outward in the slow, cold, patient movement of water across the seafloor. The oxygen content of Antarctic bottom water is also worth noting. Water that has been at the surface absorbs oxygen from the atmosphere. When that water sinks and spreads along the seafloor, it carries that oxygen into the deep ocean, where it supports the communities of organisms that live in the abyssal depths, bacteria, worms, crustaceans and other creatures that depend on dissolved oxygen in water that has not seen the surface in a very long time. Without the regular renewal of deep water through processes like the Weddell Polynya's convection, the deep ocean would gradually become more oxygen depleted. The Polynya is not just a climate feature, it is part of the system that keeps the deep ocean habitable. Carbon is part of this story as well, though the details are complicated and still being worked out. When surface water sinks into the deep ocean, it carries dissolved carbon dioxide with it. This is one of the mechanisms by which the ocean absorbs carbon from the atmosphere, not just through simple dissolution at the surface, but through the physical pump of dense water sinking and carrying carbon into the deep, where it stays sequestered for centuries. The Weddell Polynya, by driving strong convection, potentially enhances this carbon pump during active events. Whether the Polynya is a net carbon sink or source on balance is actually not fully resolved, partly because the open water surface also allows CO2 to exchange with the atmosphere in both directions, and the net effect depends on the specific conditions at any given time. This is one of the questions researchers are still working on, and it is relevant not just for understanding the Polynya, but for understanding the Southern Ocean's role in the global carbon cycle more broadly. It is worth pausing here for a moment on the sheer scale of what is being described. We are talking about a feature that forms in winter, in an area of ocean that most people will never visit, driven by a seamount on the seafloor that nobody can see, sustained by temperature and salinity differences measured in fractions of a degree and parts per thousand of salt. And yet the consequences extend to the deep ocean beneath every ocean basin on Earth, influencing water temperatures and oxygen levels and carbon content in places thousands of kilometers away. The Polynya is not a local curiosity. It is a node in a planetary system. This is also why the question of how the Polynya might change with a warming climate carries real weight. If the rate of Antarctic bottom water formation in the Weddell Sea changes significantly, either increasing or decreasing, the effects would eventually propagate through the global ocean. Changes in deep water formation rates have been linked in paleoclimate records to dramatic shifts in global climate, including some of the rapid climate transitions of the last ice age. The ocean's deep circulation is not infinitely stable. It has changed before, and the consequences of those changes were felt globally. The atmospheric effects above the Polynya are more immediate but also more localized. The heat and moisture released from the open water influence the storm systems that track across the Southern Ocean, and through those storm systems they can affect precipitation and temperature patterns across the Southern Hemisphere. Some researchers looked at whether Polynya events leave a detectable signal in the climate records of Southern South America, Southern Africa, and Australia, places that are downstream of the Southern Ocean's weather patterns. The signal is there in some analyses, though it is not always easy to separate from the noise of natural variability. The Southern Ocean is an energetic and complex system, and isolating the contribution of the Polynya from everything else that is happening is a genuine statistical challenge. What is not in question is the local effect. Above an active Polynya, the atmosphere is measurably different from what it would be over a frozen surface. The air is warmer, more humid, more turbulent. Clouds form differently. Precipitation patterns shift. The Polynya creates its own microclimate, in a sense, a persistent atmospheric anomaly anchored to the open water below it. Satellite imagery of active Polynya events often shows distinctive cloud formations above the open water, organised by the convective circulation driven by the heat flux from below. It is one of the ways that the Polynya announces itself to observing instruments from space, even before the sea ice gap itself is clearly visible. There is also the question of what happens at the edges of the Polynya, where open water meets sea ice. This boundary is an active zone of ice formation and melting. The cold air is trying to refreeze the open water. The warm, deep water rising through convection is trying to keep it open. The balance between these two forces determines the size of the Polynya from week to week. It expands when the convective heat flux dominates. It contracts when the atmospheric cooling wins. The edges are not static. They shift and breathe as conditions change, and the sea ice at the margins is in a constant state of partial melting and refreezing, producing ice with different properties than the undisturbed pack ice further away. All of this, the atmospheric heat release, the deep water formation, the carbon exchange, the oxygen ventilation of the abyss, the edge dynamics, is happening simultaneously during an active Polynya event. The feature is not simple. It is a nexus of interacting processes, each one influencing the others, each one connecting to systems that extend far beyond the Weddell Sea. The Polynya is, in a way, a place where the ocean and atmosphere are in unusually direct and intense conversation, and the content of that conversation matters for the rest of the planet. Which brings the story naturally to a question that has been sitting quietly in the background of everything we have discussed. If the Polynya is this significant, if it is contributing to global deep water formation, influencing atmospheric circulation, ventilating the deep ocean, and participating in the global carbon cycle, then understanding how it might change in a warming world becomes genuinely urgent. The ocean is not static. The atmosphere is not static. The conditions that produce the Polynya are sensitive to changes in temperature, salinity, and circulation patterns that are already shifting in measurable ways. Whether those shifts will make the Polynya more common, less common, or simply different in character is a question that researchers are now working on with considerable attention, and the answer is not yet settled. So let us sit with that question for a while, because it is one of the more genuinely difficult problems in current climate science, and it deserves more than a simple answer. The first thing to understand is that the Weddell Polynya is not controlled by a single variable. It is the product of several interacting conditions: ocean stratification, gyre circulation, storm activity, the geometry of moored rise, the seasonal cycle of sea ice. And each of those conditions is itself being influenced by a changing climate in ways that are not always pointing in the same direction. This is what makes the climate change question so hard to answer cleanly. It is not a case where warming makes the Polynya simply more likely or simply less likely. The reality is more tangled than that, and the researchers who study it are careful to say so. Start with what warming is doing to the deep ocean. The circumpolar deep water, that relatively warm, salty layer sitting below the cold surface waters of the Weddell Sea, has been accumulating heat over recent decades. Measurements taken across the Southern Ocean over the past 40 years show a clear warming trend in the intermediate and deep water layers. This is partly because the ocean has absorbed a large fraction of the excess heat trapped by greenhouse gases in the atmosphere, and a disproportionate share of that oceanic heat uptake has occurred in the Southern Ocean. The deep water is warmer than it was. Not dramatically warmer in absolute terms. We're talking about changes on the order of a fraction of a degree Celsius over decades. But in a system where the temperature difference between layers is already small, even a modest warming of the deep layer increases the potential energy available to drive convection upward. In principle, this should make Polynya events more likely. If the warm deep water is warmer than before, it has more capacity to melt ice and resist refreezing once it reaches the surface. The temperature contrast that drives the convective overturning is slightly larger. Some climate models do show an increased frequency of deep convection events in the Weddell Sea under continued warming scenarios, and the reasoning behind this prediction is physically coherent. Warmer deep water means a stronger upward heat flux once convection starts, which means the self-sustaining loop that keeps the Polynya open is easier to maintain once it gets going. But here is where the other half of the problem comes in. The surface of the Southern Ocean is also changing, not in a way that makes Polynya formation easier. The Antarctic ice sheet is losing mass. The West Antarctic ice sheet in particular has been shedding ice at an accelerating rate, and the ice shelves around the continent are thinning and in some cases collapsing. All of that melting ice releases fresh water into the ocean. Fresh water is less dense than salt water. When it mixes into the surface layer of the Southern Ocean, it makes that surface layer lighter and more buoyant, which means it floats more stubbornly on top of the warmer, saltier water below. The cold, fresh lid that normally separates the surface from the circumpolar, deep water becomes thicker and harder to disrupt. This freshwater effect is not hypothetical. Observations of the Southern Ocean over the past several decades show a measurable freshening of the surface waters, particularly near the Antarctic continent. The surface salinity has decreased. The stratification, the degree to which the ocean is layered, with lighter water on top and denser water below, has increased in some areas, and stronger stratification is exactly what suppresses deep convection. If the surface layer is more resistant to mixing, storms have to work harder to erode it, and the conditions that allow the warm deep water to punch through become harder to achieve. So you have two competing effects. Warmer deep water pushing up toward the surface with more force, and a fresher, more buoyant surface layer pushing back. Which one wins? The honest answer, as of the current state of research, is that we do not fully know. Different climate models handle these competing effects differently, depending on how they represent ice sheet melt rates, ocean mixing processes, and the sensitivity of the Weddell Gaia to changing wind patterns. Some models produce a Weddell Sea that becomes more convectively active over the coming century. Others produce one that becomes more stably stratified and less prone to Polynya events. The spread between model predictions is wide enough that researchers are reluctant to make confident forecasts in either direction. What makes this uncertainty particularly significant is that the two outcomes have very different implications for global climate. A more active Weddell Sea, producing Polynya events more frequently and generating more Antarctic bottom water, would mean faster ventilation of the deep ocean and potentially more carbon uptake in the short term. A more stably stratified Weddell Sea, with Polynya events suppressed for decades or longer, would mean reduced deep water formation, a slowdown in the global thermohaline circulation, and a deep ocean that accumulates heat and carbon more slowly, with consequences for everything downstream of that circulation. These are not small differences. They represent genuinely different futures for the ocean's role in the climate system. The 2016 and 2017 reopening of the Polynya has been examined carefully for what it might tell us about this question. Some researchers have pointed to changes in the salinity of the Weddell Sea as a contributing factor. During the decades when the Polynya was absent, the surface waters of the Weddell Sea gradually freshened, consistent with increased ice melt and precipitation. This strengthened stratification and suppressed convection. But in the years leading up to 2016, some measurements suggested a partial reversal, a modest increase in surface salinity in parts of the Weddell Sea, possibly linked to changes in sea ice patterns and wind-driven mixing. If the surface layer became slightly saltier and therefore slightly denser, the barrier between it and the warm, deep water below would have weakened, making the system more vulnerable to the kind of storm-driven disruption that apparently triggered the 2016 event. This interpretation, if correct, would suggest that the Polynya's return was not simply a random fluctuation, but a response to a specific shift in the ocean's salinity structure. A shift that may itself be connected to longer-term changes in the Southern Ocean's freshwater budget. That is a plausible story, and it fits with the physical mechanisms that researchers have identified. But it is worth being careful here. The salinity data from the Weddell Sea is sparse, particularly for the years before the Argo Float program began providing better coverage. Reconstructing what the salinity was doing in the 1980s and 1990s with confidence is genuinely difficult, and drawing firm conclusions from limited data is something the researchers themselves are cautious about. There is also the question of what role the southern annular mode plays in all of this. The southern annular mode is the dominant pattern of atmospheric variability in the southern hemisphere, essentially the degree to which the westerly winds that circle Antarctica are displaced toward or away from the pole. When the southern annular mode is in a positive phase, the westerlies strengthen and shift poleward, which has a range of effects on the Southern Ocean. It increases upwelling of deep water, it changes the rate of sea ice formation, and it affects the mixing of the surface layer. The southern annular mode has been trending toward a more positive phase over recent decades, partly in response to stratospheric ozone depletion and partly in response to greenhouse gas increases. How this trend interacts with the Polynya's behaviour is not fully worked out, but it is one of the variables that researchers are tracking. What is perhaps most striking about the climate change question, when you look at it carefully, is how much it reveals about the limits of current understanding. The Weddell Polynya is a large dramatic feature, visible from space, capable of influencing global ocean circulation studied for 50 years, and yet the question of how it will respond to a warming planet does not have a clear answer. This is not a failure of science. It is a reflection of the genuine complexity of the system. The Southern Ocean is vast, poorly sampled, and subject to multiple interacting forcings that do not always cooperate with simple predictions. The Polynya sits at the intersection of ocean physics, ice dynamics, atmospheric circulation, and deep water formation, all of which are changing simultaneously, all of which interact with each other in nonlinear ways. Some researchers have suggested that the Polynya could serve as a useful indicator, a kind of early warning signal for changes in Southern Ocean stratification and deep water formation. The idea is that if you monitor the Polynya carefully enough, its behaviour over time might tell you something about the balance between freshwater input and deep water warming, between stratification and convection that would otherwise be very hard to measure directly. A Polynya that starts appearing more frequently, or that grows larger in successive events, might signal that the stratification is weakening and the deep water is winning the competition. A Polynya that disappears again for a long period might signal the opposite. This is an appealing idea, and it has some support in the literature, but it requires exactly the kind of long-term, high-quality monitoring that has historically been difficult to maintain in the Weddell Sea. The challenge is that the Polynya does not open on a convenient schedule. It appears when conditions are right, which might be once every few decades, or it might be more often. The data record is simply too short to be sure. Researchers cannot watch it continuously in the way that, say, a weather station monitors temperature. They have to maintain a network of instruments in one of the most hostile ocean environments on Earth, waiting for an event that might not happen for years, hoping that when it does happen their instruments are in the right place and still functioning. This is the practical reality of polar oceanography, and it shapes what can and cannot be known. What has improved significantly since the 1970s is the suite of tools available for remote monitoring. The Argo Float program, which now maintains thousands of autonomous profiling floats across the global ocean, has substantially better coverage of the Southern Ocean than it did even 15 years ago. Satellite altimetry and sea surface temperature measurements provide continuous coverage of the surface. Seal tagging programs continue to add subsurface data from animals that go where ships cannot, and the models used to simulate Southern Ocean circulation have become more sophisticated, incorporating better representations of ice-ocean interaction, mesoscale eddies, and the dynamics of deep convection. None of this fully substitutes for direct observation during an active Polynya event, but it means that the next time the Polynya opens, whenever that turns out to be, researchers will be better positioned to observe it than they were in 2016. The fundamental uncertainty, though, remains. The Polynya is sensitive to conditions that are themselves uncertain. The rate at which Antarctic ice sheets will continue to melt, and how much fresh water they will deliver to the Southern Ocean over the coming decades, is one of the larger unknowns in climate projections. The trajectory of the southern annular mode depends on the interplay between ozone recovery, which tends to push the mode toward a less positive phase, and greenhouse gas increases, which tend to push it toward a more positive phase. The future behaviour of the Weddell Gyre, which controls the upwelling of deep water and the strength of the Taylor column effect over moored rees, is tied to wind patterns that are themselves changing. Each of these uncertainties feeds into the Polynya's future behaviour, and they do not resolve neatly. What researchers can say with reasonable confidence is that the Weddell Polynya is not climatically neutral. Whatever it does, whether it becomes more frequent or less frequent, larger or smaller, will have consequences that extend well beyond the Weddell Sea. The deep water it produces or fails to produce will influence the ocean's circulation and chemistry for decades. The heat and moisture it releases into the atmosphere will affect weather patterns across the southern hemisphere. The carbon it exchanges with the atmosphere will contribute, in some small but real way, to the global carbon balance. The Polynya is embedded in the climate system in ways that make its future behaviour a genuinely important question, not just an interesting scientific puzzle. And perhaps that is the most useful frame for thinking about what climate change means for the Polynya. It is not simply a question of whether the hole in the ice will appear more or less often. It's a question of how a change in one part of a tightly coupled system will propagate through that system and emerge somewhere unexpected. The ocean does not respond to warming in isolation. It responds as a system, and the Polynya is one of the places where that response becomes visible in a dramatic and measurable way. Watching what it does over the coming decades will tell researchers something important about what the Southern Ocean is doing more broadly, which is, in turn, one of the most important questions in climate science right now. The difficulty, as always, is that the Southern Ocean keeps its own counsel. It does not give up its answers easily, and the places where the most important things are happening are also the places that are hardest to reach. The Weddell Sea in winter is not a welcoming environment for human observers, and the instruments that go there in place of people have their own limitations. But the questions are clear enough, and the tools are improving, and the researchers who study this region are patient in the way that people tend to become when they are working on problems that operate on the timescale of decades. The next time the Polynya opens, and it will open again, there will be instruments in the water, satellites overhead, and scientists watching carefully, trying to learn a little more about what the ocean is doing and what that means for the rest of the planet. Which leads naturally to the question of what it actually takes to study a place like this. The physical reality of doing science in one of the most remote and forbidding environments on Earth, and the remarkable ingenuity that has gone into finding ways to gather data when direct observation is barely possible. The Weddell Sea in winter is, by almost any measure, one of the least hospitable places on the surface of this planet. That is not an exaggeration offered for effect. It is simply the physical reality of the place. Winter temperatures in the region drop to around minus 40 degrees Celsius, and that is the air temperature, not accounting for wind. The sea ice that covers the Weddell Basin during those months can reach several meters in thickness, and it moves. It shifts and compresses and ridges up into pressure formations that can be taller than a person and harder than concrete. The darkness is nearly total for months at a time. There are no landmarks, no harbours, no shelter. The nearest permanent human presence is hundreds of kilometres away. If something goes wrong out there, with a ship, with an instrument, with a person, the options for response are extremely limited. This is the environment where the Weddell Polynya forms. Not in summer, when conditions are merely difficult, but in winter, when they are genuinely brutal. The Polynya opens in the months when the sea ice is at its most extensive, when the temperatures are at their lowest, and when the Southern Ocean is generating some of the most intense storms on Earth. It appears, in other words, at exactly the moment when it is hardest to go and look at it. This is not a small practical inconvenience. It is one of the central challenges of Polynya research, and it has shaped what is known and what remains uncertain in fundamental ways. The history of human encounters with Weddell sea ice is not a gentle one. The most famous example is probably Ernest Shackleton's ship Endurance, which became trapped in the pack ice of the Weddell Sea in January 1915, and was eventually crushed and sunk by October of that year. Shackleton and his crew survived through a combination of extraordinary leadership, luck and endurance that has become one of the defining stories of polar exploration. But the Endurance was not uniquely unlucky. The Weddell Sea had a reputation for dangerous ice long before Shackleton arrived, and it has maintained that reputation ever since. James Weddell himself, the British navigator who gave the sea its name after sailing into it in 1823, encountered unusually open conditions that allowed him to reach further south than anyone had before. But those conditions were the exception, not the rule. Most of the time, the Weddell Sea does not welcome ships. Modern research vessels are considerably more capable than a wooden sailing ship from the 19th century, but they are not invincible. The RRS James Clark Ross, operated by the British Antarctic Survey, and the German icebreaker Polarstern, operated by the Alfred Wegener Institute, are among the most capable polar research ships in the world. Both have conducted expeditions into the Weddell Sea, and both have done important work there. Polarstern in particular has spent extended periods in the region, and has been intentionally frozen into the ice on research missions, most famously during the Mosaic expedition in the Arctic from 2019 to 2020, but also in Antarctic waters in earlier years. These ships can break through ice that would stop an ordinary vessel, and they carry sophisticated scientific equipment, laboratories, and the capacity to support long expeditions in remote conditions. But even these ships have limits. Operating in the Weddell Sea during winter, the season when the Polynya forms, is at the far edge of what is safely possible. The ice is thicker, the storms are more frequent and more severe, and the darkness makes navigation harder. Expeditions that do venture into the region during winter are rare, expensive, and carefully planned. The window for direct ship-based observation of the Polynya, if it happens to be open, is narrow. And because the Polynya does not announce itself in advance, planning a ship expedition specifically to observe it is essentially impossible. You cannot book a research cruise to coincide with an event that might not happen for another decade. This is where autonomous instruments become not just useful but essential. The Argo Float program, which began in the late 1990s and reached its target of 3,000 active floats by 2007, deploys profiling floats that drift with ocean currents, periodically diving to depths of 2,000 meters and measuring temperature, salinity, and pressure as they rise back to the surface. They then transmit their data via satellite before diving again. The Southern Ocean has historically been undersampled by the Argo network, partly because the sea ice interferes with satellite communication, and partly because the floats can become trapped under ice. But the program has expanded its polar capabilities over the years, and the SOCOM project, Southern Ocean Carbon and Climate Observations and Modelling, specifically deployed biogeochemical Argo floats in the Weddell Sea and surrounding waters, floats capable of measuring not just physical properties, but also oxygen, nitrate, pH, and optical characteristics. These were the instruments that provided the first detailed subsurface data during the 2016 and 2017 Polynya events, and their data was genuinely transformative for understanding what was happening beneath the surface. Still, Argo floats have their own limitations. They drift passively with the currents, which means they cannot be steered to a specific location. If a float happens to be in the right place when the Polynya opens, it will collect excellent data. If it is 50 kilometers away, drifting in the wrong direction, it will collect data from somewhere else. The spatial coverage is also inherently patchy. A few dozen floats spread across an area the size of the Weddell Basin is not the same as a continuous monitoring array. Important things can happen in the gaps between instruments and go unrecorded. Gliders offer somewhat more flexibility. Autonomous underwater gliders are torpedo-shaped instruments that can navigate through the water by changing their buoyancy and using small fins to steer. They move slowly, typically at speeds of around half a knot, but they can be directed towards specific targets and can maintain position in a region of interest for weeks or months. Several research groups have deployed gliders in the Southern Ocean, including in the waters around Maud Rise, gathering detailed measurements of water column structure in areas that ships cannot easily access. The data they return has helped fill in some of the gaps in the float-based observations, though gliders too can be lost, to equipment failure, to entanglement in ice, or simply to the difficulty of recovering them in remote waters. Perhaps the most unusual source of data from the Weddell Sea comes not from any instrument designed by oceanographers, but from animals. The MEOP program, marine mammals. Exploring the oceans pole to pole attaches miniaturized conductivity temperature depth sensors to the heads of elephant seals and Weddell seals before they are released into the Southern Ocean. The seals dive repeatedly to depths of several hundred meters in search of food, and each dive generates a profile of the water column. The sensors transmit their data via satellite when the seal surfaces. This is not a metaphor or a simplification. Researchers actually glue small instrument packages to the fur on the backs of seals' heads, wait for the animals to go about their lives in the ocean, and collect the resulting oceanographic data. The seals naturally do not know or care that they are contributing to climate science. They are simply hunting. What makes this approach genuinely valuable, beyond its somewhat improbable nature, is that seals go places ships cannot. They dive under sea ice, they travel in winter, and they cover large areas of the Southern Ocean, in the course of their normal behaviour. Weddell seals in particular are well adapted to operating in sea ice environments. They maintain breathing holes in the ice using their teeth and can remain in ice-covered areas year-round. The data from seal-mounted sensors has substantially improved the coverage of the Southern Ocean's subsurface properties during winter months, and some of the most useful measurements of water column structure in the Weddell Sea have come from animals rather than machines designed by humans. Even with all of these tools combined, ships, Argo floats, gliders, seal sensors and satellites, the observational coverage of the Weddell Sea remains sparse relative to the scale of what is being studied. The basin covers roughly 2.8 million square kilometres. The Polynya, when it opens, occupies a fraction of that area, but the processes that drive it operate across the entire basin and below it. Tracking those processes with the instrument density that is currently possible is a bit like trying to understand the weather patterns of an entire continent using a handful of weather stations scattered hundreds of kilometres apart. You can learn a great deal, and the data you collect is genuinely valuable, but there are limits to what you can see. This is why the 2016 and 2017 events were so important to the research community. They provided a real-time opportunity, the first in nearly 4 decades, to observe an active Polynya event with modern instruments. The SOCOM floats that happened to be in the region returned data that directly captured the subsurface conditions during the opening, including the weakened stratification, the upwelling of warm deep water, and the convective mixing that drove the event. That data allowed researchers to test and refine the theoretical models that had been developed during the long gap between the 1970s events and the 2016 return. It was, in the language of science, a natural experiment, not designed, not controlled, but real and observable in a way that no model simulation can fully replicate. The challenge going forward is maintaining the kind of observational infrastructure that would allow researchers to capture the next event with similar or better coverage. Argo floats have finite lifespans, typically around 5 years before their batteries are exhausted. Maintaining a network in the Weddell Sea requires continuous deployment of new floats to replace those that have died, which requires ship time, which is expensive and logistically complicated. The MEOP seal tagging program depends on access to seal colonies and the cooperation of animals that do not always behave predictably. Satellite coverage is continuous but limited to service properties. It cannot see what is happening at depth, and the models, however sophisticated, are only as good as the observations used to validate and constrain them. There is also the question of what the ice itself is doing. Sea ice extent in the Southern Ocean has been behaving in ways that have surprised researchers over the past decade. After a period of modest increase in Antarctic sea ice extent that lasted through the early 2010s, itself an unexpected trend that generated considerable scientific debate, sea ice coverage dropped sharply and dramatically in 2016 and 2017, reaching record lows. It has remained relatively low since then compared to the preceding decades. The reasons for this shift are still being studied, but they likely involve changes in ocean heat content, wind patterns, and possibly the influence of the 2015 El Niño event. What this means for future Polynya formation is unclear. Less extensive sea ice might make the region easier to observe by ship, which would be practically useful. But it also changes the conditions under which the Polynya forms, and not in ways that are simple to predict. The physical reality of doing science in the Weddell Sea, the cold, the ice, the darkness, the distance, the cost, the logistical complexity, is easy to describe in abstract terms but harder to fully appreciate without some sense of what it actually involves. Researchers who work in this region spend years planning expeditions, competing for ship time, writing grant proposals, and developing instruments capable of surviving conditions that would destroy ordinary equipment. They send their floats and gliders into the ocean knowing that some of them will not come back. They analyse data collected by seals and transmitted through satellites from one of the most remote corners of the Earth. And they do all of this in pursuit of answers to questions that most people have never heard of, about processes operating thousands of meters below the surface of an ocean that most people will never see. The Polynya forms exactly where and when it is hardest to observe. That is not a complaint, it is simply the nature of the thing. The ocean does not arrange itself for the convenience of the people trying to understand it, but it does mean that every piece of data collected from the Weddell Sea carries a weight that data from more accessible places does not. Each profile from an Argo float, each dive record from a tagged seal, each satellite image of the ice edge represents a genuine achievement of observation in a place that resists being observed. And the questions those observations are trying to answer, about what drives the Polynya, how it fits into the broader climate system, and what its future behaviour might look like, are questions that matter well beyond the Weddell Sea itself, which is perhaps what makes the remaining uncertainties feel less like frustrating gaps in knowledge and more like genuinely open problems worth pursuing. The tools are improving, the models are getting better. The next time the Polynya opens, researchers will be watching more carefully than they were in 2016, and more carefully still than they were in 1974. The answers are coming slowly, in the way that answers to large and difficult questions tend to come. And the questions themselves, what is the Polynya trying to tell us? What cycle does it follow? What does it mean for the ocean's future? Are still very much alive. So let us sit with those open questions for a moment, because they are genuinely interesting ones, and they deserve more than a passing mention. The first and perhaps most fundamental is the question of the triggering threshold. Researchers understand in broad terms what needs to happen for the Polynya to open. The stratification in the upper ocean has to weaken enough that the warm deep water below can break through, but understanding the mechanism in general terms is different from being able to predict when, specifically, the conditions will cross from stable to unstable. The ocean is not a simple system. The stratification at any given location is the result of dozens of interacting variables: temperature, salinity, wind history, the current state of the Weddell Gyre, the seasonal cycle of ice formation and melt, storm activity, and the longer-term trends in how heat and fresh water are distributed across the basin. Identifying the precise threshold at which all of those variables combine to tip the system into convection is not a problem that has been solved. Researchers can look at the conditions that preceded the 2016 and 2017 events and identify factors that seem relevant: the weakened stratification, the storm activity, the anomalously salty surface water in the region. But identifying relevant factors after the fact is not the same as knowing, in advance, how weak the stratification needs to be before the trigger is pulled. That distinction matters enormously if the goal is to predict future events rather than simply explain past ones. Part of the difficulty is that the sample size is painfully small. There have been two well-documented large-scale openings of the Weddell Polynya, the 1974 to 1976 event and the 2016 to 2017 event. That is essentially it. There may have been earlier events that predate satellite observation, and there were the smaller moored rise openings in 2000 and 2001. But in terms of full-scale Polynya events with detailed measurements, researchers are working with a data set of two. You cannot build a robust statistical model of a threshold phenomenon from two data points. You can develop hypotheses, and those hypotheses can be physically plausible and internally consistent, but they remain hypotheses in a way that is uncomfortable for a field that would prefer to have firm answers. Some researchers have proposed that the Weddell Polynya follows a roughly 20-year cycle, based on the approximately 40-year gap between the 1970s events and the 2016 return, though noting that 40 years divided by 2 is 20, which is a fairly thin basis for a cycle claim. The proposal is not unreasonable, and there are physical mechanisms that could produce multi-decadal variability. The Weddell Gyre itself oscillates in strength over long timescales, and those oscillations could modulate the conditions that favour Polynya formation. But with only two major events on record, the 20-year cycle idea is more of an intriguing possibility than an established finding. If the Polynya opens again around 2036 or 2037, That would be a meaningful piece of supporting evidence. If it opens in 2028 or 2045, or not for another 60 years, the cycle hypothesis would need to be revised or abandoned. The ocean will answer the question eventually. It just does so on its own schedule, without much regard for the timelines of the people asking. The role of moored rise in year-to-year variability is another piece of the puzzle that is still being assembled. The seamount creates the Taylor column effect, that rotating column of water that concentrates the weakly stratified conditions favourable to convection. But the strength of that effect is not constant. It depends on the speed and direction of the flow passing over the seamount, which in turn depends on the state of the Weddell gyre. When the gyre is stronger, the Taylor column is more pronounced and the region above moored rise becomes a more effective focal point for convection. When the gyre is weaker, the effect is reduced, and the conditions above the seamount may not be so different from the surrounding ocean. Researchers have documented that the Weddell gyre varies in strength over interannual and decadal timescales, driven by wind patterns over the Southern Ocean. But the relationship between gyre strength, Taylor column intensity, and Polynya probability is not yet quantified in a way that allows prediction. It is known to matter. How much it matters, and under what specific combinations of conditions it becomes the deciding factor, is still being worked out. Then there is the carbon question, which is perhaps the most practically significant open issue, and also one of the hardest to resolve. When the Polynya is open, it exposes a large area of ocean surface to the atmosphere. The Southern Ocean is generally considered a net sink for carbon dioxide, meaning it absorbs more CO2 from the atmosphere than it releases, but the balance during a Polynya event is genuinely uncertain. On one hand, cold water absorbs CO2 efficiently, and the upwelling deep water during a convection event is carrying carbon from the deep ocean toward the surface. On the other hand, the deep convection also brings nutrients to the surface, which could stimulate phytoplankton growth, which would absorb CO2 through photosynthesis. The net effect of all of these competing processes on the carbon balance of the Polynya region during an active event is something researchers are still trying to quantify. Some studies suggest the Polynya region acts as a net source of CO2 to the atmosphere during active convection, because the upwelling deep water is rich in dissolved carbon. Others suggest the biological response, the phytoplankton bloom that can follow the nutrient injection, may partially offset that outgassing. The honest answer is that we do not yet know the net carbon balance of a major Polynya event, with enough precision to say confidently whether it makes the Southern Ocean's carbon uptake stronger or weaker. Given that the Southern Ocean absorbs something like 40% of the CO2 that the global ocean takes up from the atmosphere each year, that is not a small uncertainty. A large Polynya event could meaningfully shift that balance, and not knowing in which direction is a genuine gap in understanding. There is also the question of what the Polynya does to the biology of the region over longer timescales. The Weddell Sea is not biologically barren. It supports a food web that includes krill, fish, seabirds, seals, and whales. A large Polynya event changes the light environment, the nutrient availability, and the temperature of the surface water in ways that ripple through the ecosystem. Phytoplankton blooms in Polynya regions have been documented, and those blooms form the base of the food web that everything else depends on. But the effects of a major convection event on the deeper ecology of the Weddell Sea, on krill populations, on the breeding success of seabirds and seals, on the distribution of fish, are not well studied, partly because the access problems that make the Polynya hard to observe physically also make biological surveys difficult to conduct during and after major events. This is an area where the science is genuinely thin, not because researchers are not interested, but because the logistics of doing biological surveys in the Weddell Sea in winter are formidable. What researchers are hoping the 2020s will bring is a step change in observational capacity that begins to address some of these gaps. The Argo Float program has been expanding its coverage of the Southern Ocean, and newer float designs are capable of operating under ice, a capability that earlier generations lacked, and that is obviously relevant for a feature that forms in winter, surrounded by sea ice. The biogeochemical Argo floats deployed by the SOCOM project carry sensors for oxygen, nitrate, pH, and optical properties in addition to the standard temperature and salinity measurements, which means they can provide information about carbon chemistry and biological productivity at depth, directly relevant to the carbon flux question. There are also plans within the oceanographic community to increase the density of floats in the Weddell Sea specifically, recognizing that the region is undersampled relative to its importance. If those plans are realized and the network is in place when the next Polynya opens, the quality of data available will be substantially better than what was captured in 2016 and 2017, which was already a major improvement over what was available in the 1970s. Satellite technology is also improving in ways that matter for Polynya research. Higher resolution synthetic aperture radar satellites can now image sea ice with enough detail to track the evolution of the ice edge around the Polynya on timescales of hours rather than days. New passive microwave instruments provide better discrimination between open water, thin ice, and thick ice than the instruments on Nimbus 5 that first detected the Polynya in 1974, and machine learning tools are beginning to be applied to the analysis of large satellite datasets, which may allow researchers to identify subtle, precursor signals in the ice and ocean surface that precede Polynya formation, potentially providing early warning that conditions are becoming favourable before the hole actually opens. The seal tagging program is likely to continue as well. The MEOP program has demonstrated that elephant seals and Weddell seals are genuinely useful oceanographic instruments. They dive to depths and access regions that floats and gliders cannot easily reach, and they carry their sensors through the winter months when ship-based observation is essentially impossible. The data quality from seal-mounted CTDs has improved significantly over the years, and the coverage of the Weddell Sea by tagged animals provides a kind of distributed observing network that complements the float array. There are obvious limits. You cannot control where the seals go, and they are not going to conveniently position themselves above moored rise on demand. But as a source of wintertime subsurface data from one of the most inaccessible oceans on Earth, they are genuinely valuable in a way that is hard to replicate with conventional instruments. What all of this means in practice is that the scientific community is better positioned now than at any previous time to catch the next Polynya event in enough detail to make real progress on the outstanding questions. The threshold problem, the gyre oscillation hypothesis, the carbon balance, the biological effects. None of these will be fully resolved by a single event, but a well-observed third major opening of the Weddell Polynya would provide data that could substantially narrow the uncertainty on all of them. The researchers who have spent careers studying this feature are aware of that possibility, and aware that the timing is not in their hands. The Polynya will open when the conditions are right, not when the grant cycle is convenient. There is something quietly interesting about that situation. A scientific community that has built up its tools and its understanding over 50 years, waiting for a natural event that may or may not occur within the span of a research career. The 1974 event was seen by scientists who had no framework to explain it. The 2016 event was seen by scientists who had spent decades developing a framework and were finally able to test it. The next event, whenever it comes, will be seen by scientists who have specific, well-formed questions ready and instruments in the water designed to answer them. That is how understanding accumulates, not all at once, but in layers, each generation building on what the previous one managed to observe and explain. The questions that remain open after the 2016 and 2017 events are not signs that the research has stalled. They are signs that the research has reached the point where the easy answers have been found, and the hard ones are now visible. Knowing that you do not know the triggering threshold is progress over not knowing that the question exists. Knowing that the carbon balance is uncertain is progress over not having measured it at all. The shape of the remaining uncertainty has become clearer, and that clarity is itself a form of knowledge. It tells researchers where to look next, what instruments to deploy, what models to test, and it keeps the Polynya interesting, which is perhaps not a scientific criterion but is not entirely irrelevant either. The questions that do not yet have answers are the ones that keep people sending floats into the cold, dark water of the Weddell Sea year after year, waiting for the ocean to do something that it may not do for another decade, or two, or more. What the next opening will reveal is genuinely unknown, but the researchers who study this feature are, on the whole, patient people. They have learned to be. And so we come back, finally, to the thing itself. A hole in the ice. Dark water surrounded by white in every direction, sitting in the middle of one of the most remote seas on Earth, hundreds of kilometres from the nearest coastline, in the depth of an Antarctic winter when the sun does not rise at all. It is, in some ways, a simple image, and in other ways, it is one of the most complicated things the ocean does. What the Weddell Polynya represents, when you step back and look at everything that has been learned about it over 50 years, is a reminder that the Earth climate system is not a collection of separate, tidy mechanisms. It is a single interconnected thing, and the connections run in directions that are not always obvious from the surface. A seamount 3,000 metres tall on the floor of the Weddell Sea influences a rotating column of water above it, which makes a patch of the ocean unusually vulnerable to convection, which allows warm, deep water to melt through the winter ice, which releases heat into the atmosphere, which affects storm patterns over the Southern Ocean, which feeds back into the mixing of the ocean surface, which produces some of the densest water on Earth, which sinks and spreads across the global ocean floor, which helps drive the circulation that moves heat from the tropics toward the poles and keeps the climate of the entire planet in something close to its current state. That chain of connections runs from a specific spot at roughly 65 degrees south, 3 degrees east, all the way to the deep ocean basins of the Atlantic and Pacific, and it does so through processes that operate on timescales ranging from hours to centuries. It is a lot to hold in mind. And the remarkable thing is that all of it was invisible until 1974, when a satellite carrying a microwave radiometer passed over the Weddell Sea during the Antarctic winter and sent back data showing a patch of open water roughly the size of New Zealand sitting in the middle of what should have been solid ice. The researchers who first saw that image did not have the tools to explain it. They did not have the subsurface measurements, the ocean models, the understanding of deep convection, or the concept of Taylor columns as applied to Southern Ocean dynamics. They had a strange image and a set of questions that would take the better part of 5 decades to begin answering. That gap between the first observation and a working explanation is not unusual in oceanography. The ocean is large, it is cold, it is dark below a certain depth, and it does not make itself easy to study. The history of physical oceanography is full of features that were observed before they were understood, and features that were theorized before anyone could confirm they existed. The Weddell Polynya sits somewhere in the middle of that history, observed early, partially explained gradually, and still not fully understood even now. It is an honest reflection of where the science is, and there is something reassuring about that honesty. The researchers who study this feature are not pretending to have answers they do not have. What they do have, after the 2016 and 2017 reopenings, is a substantially clearer picture of the mechanism. The deep convection model, warm salty water rising from below when the surface stratification is weakened enough, driven initially by storm mixing and then self-sustaining through the convective loop, is now well supported by data. The role of moored rise in creating a preferred location for that convection is understood in broad terms, even if the details of the Taylor column dynamics are still being worked out. The connection between the Weddell Gyre's strength and the Polynya's likelihood is established in principle, even if the precise relationship is not yet quantified. The broad outlines are there. The remaining questions are about thresholds, timing, and the interactions between the Polynya and larger systems, climate change, carbon cycling, biological productivity, that are genuinely hard to study with the instruments currently in the water. There is something worth sitting with in the sheer scale of the thing. 250,000 square kilometres of open water in the middle of winter sea ice. That is not a small anomaly. That is an area larger than the United Kingdom, sitting open in a sea that should be frozen solid, releasing heat from the deep ocean into the Antarctic atmosphere for months at a time. The heat flux from the open water surface during a large Polynya event is estimated in the range of hundreds of watts per square metre in some calculations, comparable to the energy output of a substantial industrial installation, but distributed across an area the size of a country, and driven entirely by the temperature difference between deep ocean water and Antarctic winter air. It is a staggering amount of energy to be moving through a single feature, and it is energy that would otherwise remain locked in the deep ocean, unavailable to the atmosphere. The Antarctic bottom water produced during these events is equally significant in scale. When the deep convection is active, surface water cooled by contact with the Antarctic air sinks to the seafloor and spreads northward into the global ocean basins. This water is among the coldest and densest in the world, and it forms one of the primary drivers of the thermohaline circulation, the slow global movement of ocean water that distributes heat, nutrients, and dissolved gases across the planet. The Weddell Sea is one of the main source regions for Antarctic bottom water under normal conditions, but a Polynya event can substantially increase the rate of production, sending a pulse of cold, dense water into the deep ocean that propagates outward over years and decades. Oceanographers have detected signals from past convection events in the deep water properties of the South Atlantic, thousands of kilometres from the Weddell Sea, years after the events that produced them. The Polynya leaves a trace in the ocean that outlasts the Polynya itself by a considerable margin. This is part of what makes the climate change question so genuinely difficult. If the Polynya becomes more frequent or more intense as the planet warms, the increased production of Antarctic bottom water could have effects on the global ocean circulation that are not straightforward to predict. More bottom water formation could mean more efficient transport of heat from the surface to the deep ocean, which might act as a brake on surface warming in some regions. It could also mean changes in the nutrient supply to the deep ocean, affecting biological productivity in ways that ripple through the marine food web. But if fresh water from melting ice sheets strengthens the surface stratification and suppresses convection, the opposite could happen. Less bottom water formation, a weakening of the deep circulation, and changes in the distribution of heat and nutrients that play out differently again. The models do not agree on which of these effects will dominate, and the disagreement is not a sign of poor science. It reflects genuine uncertainty about the relative magnitudes of competing processes that are both real and both operating simultaneously. What the Polynya may end up being, in the context of climate science, is an indicator. Not a simple one, and not one with an obvious interpretation, but a feature sensitive enough to the state of the Southern Ocean that changes in its behaviour, its frequency, its size, its timing, could serve as a signal of changes in the underlying conditions that are harder to measure directly. The Weddell Gyre's strength, the salinity of the surface layer, the temperature of the circumpolar deep water, the frequency and intensity of Southern Ocean storms, all of these leave their mark on whether and how the Polynya opens. A long enough record of Polynya behaviour, combined with detailed subsurface measurements, could in principle be used to reconstruct the history of those conditions and to track how they are changing over time. That is not a simple task, and the record is currently far too short to draw strong conclusions, but it is the kind of work that becomes possible once you understand the mechanism well enough to know what the feature is responding to. The researchers who have dedicated significant portions of their careers to this question are, on the whole, a patient group. They have had to be. The Polynya operated for 3 years in the 1970s, then disappeared for nearly 40 years, then came back for 2 years in 2016 and 2017, and has since returned to its quiet absence. The next major event could come in 5 years or in 25. There is no reliable way to predict it, only to monitor the conditions that make it more or less likely, and to have instruments in place when it happens. The SOCM floats are there. The seal-mounted sensors are being deployed each season. The satellites are passing overhead with better instruments than the ones that first detected the Polynya half a century ago. The monitoring network is, by historical standards, reasonably good. Whether it will be good enough to capture the next event in full detail depends partly on when that event occurs and partly on whether the floats happen to be in the right positions when the convection begins. There is something quietly moving about that picture, if you let yourself think about it for a moment. Somewhere in the Weddell Sea right now, in water that is close to freezing and dark for months at a time, autonomous instruments are drifting through the water column, measuring temperature and salinity and oxygen and pH, sending their data up to satellites when they surface, and then diving back down to continue their slow circuits. They have no way of knowing whether the Polynya will open this year or next year or in a decade. They are simply there, measuring, because the people who designed them and deployed them understood that the ocean does not announce its intentions in advance, and that the only way to catch something when it happens is to already be watching. That kind of patient distributed attention is, in a sense, what modern oceanography looks like. It is not dramatic. It does not produce results quickly. It requires a long-term commitment to maintaining observing systems in places that are expensive and difficult to reach, on the chance that something important will happen while the instruments are running. The Weddell Polynya has justified that commitment more than once. The 2016 and 2017 events produced papers that substantially advanced the understanding of Southern Ocean dynamics, and the next event will almost certainly produce more. The investment in monitoring pays off eventually, even if the return comes on the ocean's schedule rather than the researchers, and maybe that is the thing worth holding on to at the end of all this. The Weddell Polynya is not a problem to be solved and set aside. It is a recurring feature of a living ocean, one that has been doing what it does for far longer than anyone has been watching, driven by processes that were operating long before there were satellites, or Argo floats, or research vessels, or any human awareness of the Southern Ocean at all. The seamount was there, the gyre was turning, the deep water was warm and the surface was cold and the stratification was sometimes thin enough to break. The Polynya opened and closed on its own schedule for reasons that had nothing to do with anyone's curiosity about it. We arrived late to the observation of it, and we are still in the early stages of understanding it, and that is fine. That is where the science actually is. What the story of the Weddell Polynya offers, beyond the specific details of ocean physics and satellite imagery and seamount fluid dynamics, is a kind of perspective on the scale of the Earth's systems and the pace at which they operate. A feature that persists for 3 years, disappears for 40, and returns for 2. On a timescale like that, 50 years of scientific observation is barely the beginning of a record. The ocean is patient in a way that human institutions rarely are, and studying it requires accepting that some questions will take longer than a career to answer, that some events will happen between funding cycles or after retirements, that the data you spend years collecting may end up being most useful to someone who has not yet started graduate school. That is not a comfortable position for anyone who wants to see their work completed, but it is an honest one, and the researchers who have built the observing systems and developed the theoretical frameworks have done something genuinely valuable, regardless of whether they are the ones who eventually close the remaining gaps. The hole in the ice will come back. It has done it before, and the conditions that produce it have not gone away. Moored Rise is still there, rising 3,000 metres from the seafloor. The Weddell Gyre is still turning. The circumpolar deep water is still warm relative to the surface. The ingredients are all present. What changes from year to year is whether the surface stratification is thin enough, whether the storms are strong enough, whether the Taylor column above the seamount is in the right configuration to concentrate the vulnerable water in the right place at the right time. When those things align, and they will eventually, the dark water will open again in the middle of the winter ice, and the instruments will begin recording, and the researchers will begin analysing, and the understanding will move a little further forward than it was before. That is a slow kind of progress. But it is real progress, built on decades of careful observation and honest uncertainty, and it is the kind that tends to last. Thank you for spending this time with the Weddell Polynya and with Life Beyond Seen. If any part of this story stayed with you, the seamount, the satellite image from 1974, the seals carrying instruments through the winter ocean, or just the simple image of dark water surrounded by ice in the middle of the Antarctic winter, I would genuinely love to hear which part in the comments below. These are the kinds of topics that tend to leave people with one detail that just sticks, and I am always curious which one it is for different people. If you have not already, a like on this video helps more people find their way to stories like this one, and subscribing means you will be here for the next one. Take care of yourselves, wherever you are tonight, and sleep well.